Hello, and welcome to a quiet exploration of one of the most captivating ideas in theoretical physics and astroengineering. Tonight, we will wander through the calm science behind Dyson spheres, those imagined megastructures that circle distant stars and harvest their enormous radiant energy. This is not a story of rockets or explosions or science fiction fantasy, but rather a careful journey through the physics, mathematics, and engineering principles that make these structures theoretically possible. A Dyson sphere represents humanity's attempt to imagine how a civilization vastly more advanced than our own might solve the problem of energy scarcity on a stellar scale. We will explore how the idea emerged from the mind of a physicist who, by his own admission, thought the whole thing was somewhat of a joke. We will examine why the popular image of a solid shell surrounding a star is physically impossible, and why distributed swarms of collectors make far more sense. We will discover how energy flows from distant stars across the vacuum of space, how civilizations might harness it, and what traces such massive undertakings might leave for us to detect. Most importantly, we will do all of this with the understanding that these ideas emerge from genuine scientific thinking, grounded in real physics and real constraints. If you enjoy these quiet journeys through science and possibility, I invite you to like, subscribe, or share a thought in the comments below. For now, let us turn our attention outward, toward the stars. Freeman Dyson was a British-American theoretical physicist and mathematician who worked in quantum field theory, astrophysics, and engineering. Born December 15, 1923, he became Professor Emeritus at Princeton's Institute for Advanced Study. His diverse intellectual work made him uniquely qualified to bridge theoretical physics and practical engineering. Beyond Dyson spheres, he contributed foundational ideas that shaped modern physics. His Princeton position allowed him freedom to pursue speculative ideas. In 2003, Dyson revealed something surprising. The paper was intended largely as a joke and unrelated to his serious work. He found it amusing that he had become famous for an idea he hadn't taken entirely seriously. This candid admission shows how groundbreaking scientific concepts often emerge from intellectual playfulness rather than solemn formal research. What Dyson actually proposed in 1960 differed greatly from popular imagination. He wrote that a solid shell surrounding a star is mechanically impossible. His vision consisted instead of a loose swarm of objects in independent orbits. This distinction has become crucial as the idea spread through culture. He imagined objects that could masquerade as dust from a distance, but his word choice, particularly biosphere surrounding the star, sparked an accidental legacy. Science fiction writers imagined the biosphere as a complete sphere encircling the star. This fundamental divergence shaped public perception ever since. The term swarm more accurately captures Dyson's vision than sphere, which implies a continuous, complete structure. Understanding this distinction is essential to understanding why modern scientists differentiate between theoretical shells and practical swarms. Science fiction imagines a solid Dyson sphere as a complete shell surrounding a star. Real physics tells a different story. A rigid, hollow shell centered on a star is not gravitationally stable like planets. It must be held by active force or it drifts inward. Even slight displacement causes gravity to pull it toward the star with no restoring force. This instability means infinitesimal perturbations cause catastrophic failure. A complete shell would be vulnerable to asteroid and comet impacts traveling at tens of kilometers per second. The large collision could break it, sending fragments into the Sun. The material needed to withstand such stresses would be extraordinarily demanding. A solid shell would also block light and heat from the star, creating a cold, dark interior that defeats the purpose. These multiple failure modes explain why serious discussions abandoned the shell concept in favor of independent collector swarms. Stars radiate enormous energy continuously in all directions. Our Sun outputs about 386 billion megawatts every second. This enormous energy spreads equally in all directions, so only a tiny fraction reaches Earth at 93 million miles away. A Dyson swarm built much closer to the star would intercept far more energy per collector area. The farther from the star, the less energy is received because total energy spreads over a larger spherical surface. Conversely, closer collectors receive more densely concentrated energy and can capture more power from smaller collector areas. Different stars release different amounts depending on size, temperature, and composition. Dyson addressed a simple but profound problem. Planets intercept only a tiny fraction of their star's energy. Any civilization needing more power than a planet supplies must harness stellar energy differently. By building structures encircling the star, a civilization could theoretically capture almost all radiated energy. Distances in our solar system are measured in astronomical units, or AU. 1 AU is Earth's average distance from the Sun, about 93 million miles. Mercury orbits at 0.39 AU, Venus at 0.72 AU, Earth at 1 AU, and Mars at 1.52 AU. A Dyson swarm would be built much closer than Mercury, perhaps 0.1 to 0.5 AU from its star. This is close enough to capture substantial energy, but far enough to manage intense radiation and heat. The choice of orbital distance involves trade-offs between energy density and thermal management. Some proposals suggest using multiple rings at different distances, creating nested layers of collectors. Stars broadcast energy in all directions continuously. Our Sun could provide all humanity's current needs thousands of times over if we captured its output. But we intercept only a minuscule fraction. This waste bothers engineers fundamentally. Why allow such tremendous power to stream unused into space when it could be harnessed? Planets intercept only energy falling on their cross-sectional area. Advanced solar collectors cannot gather energy when the Sun is below the horizon or obscured by clouds. A civilization limited to planetary energy harvesting will eventually find its population constrained by available power. A Dyson structure solves this. By spreading collectors around the star instead of on a single planet, a civilization could capture energy continuously from nearly all directions. This energy could be gathered, stored, and transmitted wherever needed. This represents the fundamental appeal of Dyson structures. Human civilization has experienced exponential growth in energy consumption as technology advances. Coal powered the Industrial Revolution, oil and natural gas shaped the 20th century. Today we transition toward renewable sources. As civilizations advance, energy requirements grow, population expands, requiring more resources. Technology creates new uses for energy in computing, transportation, manufacturing, and communication. Industrial processes become more sophisticated and energy-intensive. Climate control requires substantial power. Eventually, a civilization using planetary energy sources reaches a plateau where growth is constrained by available homeworld energy. At that point, a spacefaring civilization must look outward. They build space habitats requiring life support energy. They develop industries consuming power. They eventually harness their star's energy directly through megastructures. The Kardashev scale, proposed in 1964, classifies advanced civilizations by energy harnessing capabilities. Type 1 harnesses all energy on a single planet, controlling weather and earthquakes. Type 2 controls all energy from its parent star, typically through Dyson structures. Type 3 harnesses an entire galaxy's energy. Each step represents a billion-fold increase in available energy. The energy difference between Type 1 and Type 2 is roughly equivalent to the difference between current humans and Type 1. The scale shows how advanced a Dyson-building civilization would need to be. It highlights the immense gap between humanity's current capabilities and what is required. Building Dyson structures defines achieving Type 2 status. Type 1 civilizations master all energy resources of an entire planet, controlling weather patterns and harvesting all available sources. They would have weather control, preventing earthquakes and volcanic eruptions. They would exploit geothermal, tidal, and solar energy far more efficiently than we do. Humanity rates approximately Type 0.73, less than 3/4 of Type 1. We do not fully control energy resources, nor prevent natural disasters. Type 2 civilizations harvest the total energy output of their star. They would have populations in the trillions, distributed across vast networks throughout their star system. Their technology might appear magical to our understanding. They could transmit power across their star system using directed energy beams. Type 3 civilizations harness entire galaxies. Understanding these levels helps recognize the tremendous distance between our current position and a Dyson-building civilization. Why Dyson chose a swarm rather than a shell is obvious. A swarm of independent objects offers decisive advantages over a single shell. Each object orbits independently, following Kepler's laws like planets, so orbital mechanics are stable. A swarm builds gradually as resources and technology allow, rather than requiring one massive construction effort. If individual collectors are damaged, the rest continues functioning. Each collector maintains its orbit through its own propulsion system, allowing course corrections and avoiding drift problems. Swarms are robust against asteroid impacts. Damage to one collector doesn't cascade through the structure. Dyson stated individual objects could masquerade as dust, making the structure indistinguishable from natural cosmic debris. This elegant solution demonstrates why his vision proved far more scientifically credible than science fiction's solid shells. Orbital mechanics governs how objects move around stars and planets. Newton's law of universal gravitation describes gravitational attraction. Kepler's laws describe orbits followed by planets and satellites. Objects orbiting a star follow elliptical paths with the star at one focus. Orbital speed depends on orbit size and star mass. Closer orbits move faster, As long as an object travels at the correct speed for its distance, it continues indefinitely without additional thrust. Orbital stability is a fundamental feature of gravity. Planets have circled stars for billions of years following nearly identical paths. A Dyson swarm would consist of billions or trillions of objects, each maintaining its own orbit around the host star, following Kepler's laws. How satellites stay in orbit is physics. A satellite in continuous freefall toward a star is balanced by horizontal motion. Imagine throwing a ball horizontally. The ball falls due to gravity while moving horizontally. If the ground was spherical and the ball thrown fast enough, it would fall at the same rate the ground curves away. This is orbit. A satellite maintains altitude not by fighting gravity, but by moving fast enough that its curving path follows the space around a massive body. At any distance from a star, exactly one speed allows stable orbit. This balance between gravity pulling inward and motion carrying outward creates stable orbits. A Dyson swarm relies on this principle, with each collector moving at the right speed for its distance, maintaining stable orbits. Lagrange points are special locations where gravitational forces balance, allowing objects to remain relatively stationary with respect to two bodies. The most famous is L1, located between a star and planet, where gravitational pulls balance. The James Webb Space Telescope sits at the L2 Lagrange point of the Earth-Sun system. In a Dyson swarm, Lagrange points might position equipment or create stable zones without active propulsion. However, they represent only part of a swarm's architecture. Most collectors would orbit regularly following Kepler's laws. Lagrange points support infrastructure like construction facilities and repair stations. A rigid shell surrounding a star faces multiple fatal problems. A shell is not in orbit. Gravity's pull on an orbiting object is balanced by its motion. But a shell doesn't move fast enough to orbit. It would sink gradually towards the star. The shell is unstable against small perturbations. Displacement from centering causes gravity to pull it towards the star with no restoring force. It must survive asteroid impacts traveling at tens of kilometers per second. A large collision could break it and send fragments into the star. It would need to be incomprehensibly massive to support its own weight. No known material is strong enough without complex internal supports. Material requirements would exceed total planetary mass, requiring destruction of entire planetary systems just to gather enough material. Material strength requirements for Dyson structures are profound. Steel has excellent strength-to-weight ratios, but even it has limits. A Dyson shell would need to support gravitational shear stresses that develop as gravity pulls unevenly on different parts. These stresses could exceed any known material's capacity unless impossibly thick. A shell thick enough would be so massive it would require complete disassembly of multiple planets. As material thickens, gravitational forces increase, making the problem worse. A distributed swarm avoids this entirely because each collector is small enough that gravity's force is manageable using conventional materials. This is why Dyson's swarm concept is vastly more feasible than the shell. Fiction often gets Dyson spheres wrong because compelling storytelling differs from physical reality. A solid sphere completely encircling a star is visually striking and easy to imagine. It implies complete engineering triumph. A swarm of billions of distributed objects is harder to visualize. The fictional shell allows stories about interior surface habitation with artificial ecosystems. These narrative possibilities make solid shells appealing to fiction writers despite physical impossibility. The swarm concept is less inspiring fictionally. It lacks the grand unified architecture. There is no clear boundary between inside and outside. Yet the swarm is what Dyson proposed and what modern science focuses on. Fiction and reality differ. The swarm concept is far more sophisticated than a random collection of objects. Each collector is a spacecraft with large solar surfaces and systems to convert captured energy. Collectors are arranged in orbital shells around the star at specific distances. Density is calculated based on civilization needs and collector output. Millions or billions of units are placed in carefully tuned orbits to form star-encircling collectors. This modular growth is far more feasible than building a complete shell simultaneously. A civilization begins with a single ring or collector, testing technologies and developing expertise. As capabilities improve, more collectors are added. After centuries or millennia, the swarm might encompass most orbital space around the star. Partial coverage provides enormous energy benefits. Individual collector design is driven by capturing stellar radiation and converting it into energy while managing intense heat. Each collector has large solar panel arrays, vastly larger than spacecraft solar panels today. A single collector might span kilometers. Collectors need heat dissipation systems to radiate waste heat. They require propulsion systems to maintain orbit and adjust position. They need communication systems to coordinate with other collectors. They require structural supports against mechanical stresses and cosmic debris impacts. Different designs optimize for different purposes. Some focus on maximum efficiency, others prioritize durability. Still others perform specialized functions like beam transmission. Overall design balances energy capture efficiency, structural integrity, reliability, and resource constraints. Solar sail technology captures energy from stellar radiation and uses that energy to maintain orbits. A solar sail has large reflective surfaces that catch radiation pressure from a star's light. Photons exert small but steady force used to move the spacecraft or maintain orbit. Solar sails need no fuel. They use the star's radiation to power motion. In a Dyson swarm, solar sails capture energy and use radiation pressure for useful work. The force is small but persistent, and when applied over vast areas, becomes significant. A Dyson swarm could use solar sail technology extensively, converting stellar radiation directly into mechanical motion. However, solar sails have limitations. Radiation pressure is weak compared to gravity. Additional propulsion systems might be needed. Despite this, solar sails represent elegant technology for Dyson swarm infrastructure. Photovoltaic technology powers solar panels on rooftops today and could be expanded to stellar scales. Photovoltaic cells convert light directly into electricity through the photoelectric effect. Modern panels achieve 20% to 22% efficiency. A Dyson swarm using this technology would need similar efficiency at vastly larger scales. Collectors would be enormous arrays oriented towards the star connected to electrical distribution systems. Main challenges are scaling up manufacturing and developing efficient power transmission. Alternatively, collectors could use solar thermal systems where sunlight heats fluid driving turbines. Thermal systems might achieve higher efficiencies. The choice between technologies depends on engineering trade-offs and target star characteristics. Heat management in space differs from planetary surfaces. There is no atmosphere to carry heat away. The only way to dissipate heat is through radiation into the vacuum of space. All matter above absolute zero radiates thermal energy, described by the Stefan-Boltzmann law. A Dyson collector must be kept at a manageable temperature through careful radiative surface design. The collector captures stellar radiation and converts much to electricity. Energy not captured, plus conversion waste heat, must be radiated away. If too hot, materials are damaged. If it radiates too much, it's not capturing designed energy. The balance between energy input, conversion, and waste heat radiation determines operating temperature. Infrared radiation is essential to understanding Dyson collector operation and detection. The electromagnetic spectrum ranges from radio waves through visible light to gamma rays. Infrared falls between visible and radio, around 700 nanometers to 1 millimeter wavelength. It is thermal radiation. Moderate temperature objects emit most thermal radiation as infrared. A Dyson collector re-radiating waste heat emits much as infrared. Collector temperature determines its emission wavelength. A collector at a few hundred Kelvin emits thermal infrared, around 10 to 100 micrometers. This differs from starlight peaking in visible spectrum for sun-like stars. This wavelength difference is crucial for detection. A distant observer would see unusual infrared excess from a star surrounded by a Dyson swarm. The star shines in visible light, but Dyson collectors re-radiate as infrared. This infrared excess is anomalous and distinctive, serving as a potential technosignature. Dyson structure thermodynamics follows fundamental universal laws. The first law states, energy cannot be created or destroyed, only converted. The second law states, energy conversion produces lower quality forms, typically heat. When a collector captures radiation and converts it to electricity, some input energy becomes waste heat. This waste heat must be disposed of. In space, the only disposal mechanism is thermal radiation. According to the Stefan-Boltzmann law, an object radiates power proportional to its temperature to the fourth power. A swarm in thermodynamic equilibrium radiates all received energy or it heats indefinitely. Operating temperature depends on balance between received and radiated energy. More intense radiation means higher temperature. Temperature determines the wavelength of most radiated energy. Perfect efficiency is impossible due to thermodynamic laws. Even theoretically high-efficiency collectors lose energy as heat. Real-world systems are limited by multiple factors. Photovoltaic systems are limited by semiconductor bandgap. Photons with less bandgap energy are wasted. Thermal systems are limited by temperature difference via Carnot's law. All systems lose energy to resistance, friction, and imperfect conversion. A Dyson swarm might achieve 50% efficiency, capturing half of incident radiation. Even so, 50% or more of incident energy becomes waste heat radiation. For a sun-like star over vast areas, waste heat would be enormous. making thermal radiation management a primary engineering challenge. Perfect efficiency is forbidden by the laws of nature. Waste heat is the most reliable detection method for identifying Dyson structures around distant stars. Dyson himself proposed this infrared detection method in his 1960 paper. A star without megastructures shines with its characteristic surface temperature spectrum. A sun-like star emits primarily in visible range, a Dyson swarm absorbing that light and re-radiating it as infrared creates distinctive infrared excess. Astronomers compare observed infrared flux to expected amounts based on visible spectrum. Stars showing far more infrared than predicted could have Dyson structures. The waste heat signature is nearly impossible to hide. It's a thermodynamic consequence. A civilization using stellar energy must radiate waste heat, and hiding it would require remarkable engineering. The infrared signature serves as a techno-signature, evidence of advanced civilization that physicists search for in distant star surveys. The habitable zone is where liquid water could exist on a planetary surface. For sun-like stars, this zone extends from about 0.95 to 1.37 AU. Habitable zones vary for different star types. A Dyson swarm must avoid interfering with potentially habitable planets. If a civilization builds a swarm with existing planets in the habitable zone, it must avoid shadowing those planets or altering thermal environment dramatically. However, a civilization building a Dyson swarm might view planets as obstacles rather than treasures. A sufficiently advanced civilization might relocate planets, adjust orbits, or harvest them for raw materials. Habitable planets don't preclude building a Dyson swarm, but they add complexity and constraints. A civilization committed to Type II status might not preserve habitable planets. Orbital location determines energy density and operating conditions. Collectors could orbit from 0.1 AU very close to farther distances. Energy intensity decreases with the square of distance, following the inverse square law. At 0.1 AU, energy intensity is 100 times greater than at 1 AU. Close collectors intercept more energy but need heat management. Far collectors need larger areas for the same power. A swarm might use multiple orbital shells at different distances with different collector types. Innermost shells use specialized heat-resistant collectors. Outer shells use standard collectors. This nested design captures wide energy densities while matching designs to environmental conditions. Architecture is optimized for the target star and civilization's capabilities. A mature Dyson swarm specializes collectors for various functions. Some focus on maximum energy conversion efficiency and transmit power to collection points. Others at greater distances operate at lower temperatures better for certain conversions. Still others serve as structural elements, beam transmission stations, or manufacturing facilities. Some collectors concentrate solar radiation using lenses or mirrors, creating hot focal points for industrial processes. Others have large radiative surfaces optimized for cooling specific systems. The flexibility allows specialization and optimization in ways a single unified structure cannot match. A mature swarm would be a complex patchwork of specialized structures arranged to balance energy capture, transmission efficiency, and operational requirements. The overall system functions as an enormous distributed power plant spanning an entire star system. Distance and energy intensity represent a fundamental design constraint. Close to the star, collectors receive extremely intense radiation, allowing small areas to capture enormous power. However, they need exotic materials and sophisticated thermal management, making them difficult and expensive. Far from the star, collectors receive less intense radiation, needing larger areas for the same power. But they use conventional materials and simpler thermal management, making them easier and more reliable. A civilization must balance advantages of high intensity at close distances against engineering advantages at greater distances. The choice depends on technological capabilities and swarm project goals. The inverse square law states radiation intensity decreases with the square of distance. Doubling distance reduces intensity to 1/4. Tripling distance reduces it to 1/9. This applies to all radiation. Radiation spreads equally in all directions, distributing power across larger spherical surfaces with distance. At distance r, intensity is proportional to 1/r squared. Being twice as close provides 4 times the intensity. Being 10 times closer provides 100 times the intensity. A collector very close to a star receives far more energy than one positioned far away. The innermost Dyson swarm parts capture the most energy and are most valuable. Outer parts capture less but operate in less harsh conditions. The inverse square law is crucial to Dyson structure design. It dictates energy density at any distance from the star. It determines collector area sizes needed for target power at various distances. It shapes the thermal environment. It influences construction economics. Inner regions capture more energy from smaller areas but require advanced technology. A civilization would likely start with a single orbital ring at intermediate distance where energy density is useful. But thermal challenges aren't extreme. As technology improved, they would expand inward with advanced collectors or outward with diminishing returns. A mature swarm's shape and density distribution would reflect these trade-offs, with denser concentrations at optimal distances and sparser coverage farther out. The inverse square law shapes the entire swarm's architecture. Calculating optimal collector placement balances multiple factors to maximize efficiency and usability. A civilization would consider energy intensity at each distance, technological requirements, thermal load capacity, and strategic goals. One approach positions the first ring where energy intensity is high enough but doesn't require exotic materials. For a Sun-like star, this might be 0.20.5 AU from the star, 10 to 20 times closer than Earth. At such distances, energy intensity would be 100 to several hundred times greater than Earth receives. As technology improved, the civilization might add rings closer and farther, creating a nested structure. Optimal spacing depends on total collector numbers and power needed. Different civilizations might choose different solutions based on unique circumstances. Planetary orbits are important considerations for swarm placement, though planets would be minor obstacles at Dyson scale. If a system has planets, a swarm must have gaps or sparse regions where planets orbit. The scale of Dyson swarms is so vast that planetary interference would be minor. A planet like Jupiter is millions of times less massive than the Sun, affecting only its immediate vicinity. A swarm with billions of collectors has many ways to route around planets. The main concern is whether to preserve planets if their material is needed for the swarm. In the long term, a civilization might view planets more as raw material than obstacles. Planets represent only minor complications for swarm design. The problem of shadowing occurs when collectors in an inner orbit block starlight from reaching collectors in an outer orbit, reducing the energy capture efficiency of the outer collectors. Imagine standing in the shadow of a building on a sunny day. The shadow is a region where the building blocks sunlight from reaching the ground. In a Dyson swarm, if collectors in a close orbit block the radiation from reaching collectors in a farther orbit, then the outer collectors are being shadowed. This reduces their ability to capture energy and makes their position less efficient. The amount of shadowing depends on the density of collectors in the inner orbit, their size, and the separation between inner and outer orbits. If the inner orbit is very sparsely populated, most radiation passes through without being blocked, and shadowing effects are minimal. If the inner orbit is densely populated, significant shadowing occurs. A well-designed Dyson swarm would minimize shadowing by carefully calculating the density of collectors at each orbital distance. The densest coverage would likely be at optimal distances where the balance between energy intensity and technology requirements is best. The coverage would become sparser at greater distances where each collector must be larger to capture the same amount of energy, and at smaller distances where only advanced collectors can function. The geometric considerations of shadowing would be one of many factors influencing the final design of a mature Dyson swarm, but it would not be a fundamental barrier to construction. How a swarm self-organizes reveals the distributed nature of system architecture that makes swarms practical. Unlike a rigid shell that must be constructed as a single integrated unit, a swarm can grow organically, with individual collectors being added one at a time as a civilization's capacity allows. Each new collector can be placed in orbit at the location most suitable for its position in the overall architecture. The swarm grows from a few initial collectors to more and more, gradually filling in the orbital space around the star. The self-organizing property emerges naturally from the fact that each collector is independent and only needs to maintain its own orbit. There is no requirement for the overall structure to be complete or uniform. The swarm can remain functional and useful even if it is only partially constructed, capturing and transmitting power from whatever collectors exist. This is a stark contrast to a shell, which would need to be essentially complete to be structurally stable. The self-organizing growth of a swarm makes it inherently more practical as a construction project for a civilization developing over centuries or millennia. Early stages of swarm construction would involve launching the first few collectors and developing the infrastructure to power them and transmit their energy. Middle stages would involve systematic expansion, adding more collectors at optimal orbital distances. Later stages would involve filling in gaps, optimizing collector positioning, and perhaps extending the swarm to greater distances as technology improved. The growth would likely follow exponential or near-exponential patterns, with growth accelerating as the initial swarm collectors generated abundant power for further construction. Station-keeping requirements for collectors in a Dyson swarm involve maintaining orbital position despite various perturbations and forces that would gradually alter their orbits if left unmanaged. Orbital mechanics tell us that in a perfectly spherical system with no external forces, an object in orbit would maintain its orbit indefinitely, circling the star in the same path eternally. However, real star systems are not perfectly spherical and smooth. Stars have magnetic fields, stellar wind streams outward, carrying charged particles that interact with satellites. Gravitational perturbations from planets and other collectors create small forces that gradually alter orbits. Radiation pressure from the star exerts forces on reflective surfaces. Collisions with dust particles and small meteor oroids impart impulses that change orbital trajectories. Over months and years, these small forces accumulate and alter the orbit of any collector. To maintain its desired orbital position, each collector would need a propulsion system capable of making corrections. These corrections might be modest, small burns of chemical thrusters or solar sail adjustments to counteract perturbations. A collector's propulsion system might use fuel, ion drives, solar sail techniques, or some combination. The propulsion system would need enough capacity to maintain orbital station for years or decades, the expected operational lifetime of the collector. As collectors age and their propulsion fuel depletes, they would either need to be refueled during maintenance operations or be replaced with new collectors. Station keeping represents an ongoing operational cost for a Dyson swarm, but it is manageable with technologies that are well within the realm of plausible advanced engineering. Active versus passive orbital maintenance represents a choice in how collectors would be managed to maintain their orbital positions over time. Passive maintenance would rely on the natural dynamics of orbital mechanics and careful initial positioning to minimize the rate of orbital decay. A collector placed in a carefully chosen orbit and balanced against various forces might maintain its position for many years before perturbations become significant. This approach minimizes fuel use and operational complexity. However, passive maintenance would eventually require maintenance or replacement as orbits degraded. Active maintenance would involve continuous or regular adjustments using propulsion systems to counteract perturbations as they occur. This approach requires more fuel and more sophisticated systems, but it maintains precise control of collector positioning at all times. An advanced civilization building a Dyson swarm would likely use a combination of both approaches. New collectors might be positioned using careful orbital mechanics to minimize initial perturbations. Over their operational lifetime, they would require periodic active maintenance to correct orbital drift. Eventually, as propulsion fuel depleted or components wore out, collectors would be replaced or refueled during maintenance missions. The overall system would function as a dynamic network, with individual collectors constantly being adjusted, maintained, and replaced to keep the swarm functioning as a cohesive energy collection infrastructure. What Dyson actually proposed extended beyond simple swarms into several intriguing variations that engineers have explored. One such concept is the Dyson bubble, a structure using radiation pressure from the star to maintain equilibrium. Imagine standing in a solar wind where light streams outward carrying momentum. A thin reflective shell positioned at the right distance experiences outward pressure from stellar radiation balanced against inward gravity. This equilibrium allows the shell to remain stable without propulsion systems. The beauty of a Dyson bubble lies in its elegance. Rather than requiring active station keeping, it maintains position through fundamental physics. The concept demonstrates how creative engineering works with natural forces rather than against them. Some theorists suggest Dyson bubbles might be more practical than swarms. A reflective surface oriented properly could capture and utilize radiation pressure in remarkable ways. Light pressure exerts real force on objects, though subtle at human scales. When photons strike a surface, they transfer momentum. A solar sail exploits this, using radiation pressure to accelerate without fuel. Collectors could be designed as large, lightweight reflective surfaces. Billions of photons per second provide steady, continuous thrust. Unlike chemical rockets, solar pressure provides perpetual acceleration. The force is gentle but persistent, like constant wind on a sail. Over weeks and months, pressure accumulates into meaningful velocities. A collector positioned correctly experiences outward radiation pressure that partially offsets gravity. This reduces effective gravity binding the collector to the star. Understanding radiation pressure is crucial to comprehending how some Dyson structures remain in position. Solar sails as statites represent a next step beyond passive collectors. A statite hovers at a fixed position relative to a star without orbiting, using radiation pressure to balance gravity entirely. A collector designed as a statite remains perfectly still relative to the star rather than following orbital paths. This offers advantages for construction and maintenance. Workers approach without calculating orbital mechanics. Resupply becomes simpler without orbital velocity to match. Repair teams station themselves at fixed locations. The drawback is that statite design requires precise surface reflectivity. Any imperfection causes drift corrected by propulsion. Some collectors might combine statite principles with conventional thrusters. In a Dyson swarm, statite collectors would remain at fixed positions, creating a stable lattice. Non-Keplerian orbits describe paths violating usual orbital mechanics, creating possibilities for Dyson structures. Spacecraft using continuous low-thrust propulsion follow paths impossible for unpowered objects. A collector using ion engines or solar sails adjusts its trajectory continuously. Instead of circular orbits, it maintains complex paths. It might hover, spiral inward or outward, or follow unusual patterns. Solar sail technology enables non-Keplerian orbits through constant acceleration. Collectors could remain stationary relative to the star. Multiple collectors maintain formation flying with precise distances and angles. These orbits offer flexibility for arranging Dyson structures. Some collectors form rings while others form three-dimensional lattices. Advanced civilizations would exploit these possibilities extensively in Dyson design. The Dyson net concept reimagines the swarm as an interconnected web rather than independent objects. Collectors link via cables, beams, or force fields, distributing stress and creating stability. Nodes positioned at regular intervals connect via load-bearing tethers. This provides swarm benefits while adding structural coherence. The net maintains flexibility while providing more structure than random swarms. Materials for tethers must be extraordinarily strong yet lightweight. The Dyson net resists partial damage as remaining portions function. Distributed weight spreads across connection points, reducing stress. Construction involves positioning nodes first, then extending connections. Maintenance crews traverse the net directly. The concept represents middle ground between radical network architecture and independent swarms. Ring-based designs offer another practical approach to Dyson megastructure construction. Collectors organize into rings at specific distances from the star, rather than random distribution. Ring structure creates geometric order and simplifies management. Each ring orbits at consistent altitude like planetary rings. Multiple rings stacked at different distances eventually cover most orbital space. Constructing rings progressively allows incremental expansion and technology testing. Ring geometry simplifies engineering. Collectors within rings maintain constant distances. Navigation and collision avoidance become predictable. Supply lines follow ring geometry. Rings align in equatorial plane or tilt, depending on preferences. Multi-ring designs with tilted rings create three-dimensional lattices. Ring-based structures emerge naturally as civilization expands stellar energy harvesting. Partial coverage strategies acknowledge that civilizations may not need complete stellar energy capture. Capturing all energy from a star requires vast resources and centuries. Many applications need only a fraction of stellar energy. A civilization might build collectors capturing 10 or 20% of output. This provides enormous energy while requiring fewer resources. Partial coverage takes many forms. Collectors concentrate in equatorial regions or distribute sparsely across all orbits. Some focus on specific star quadrants for regional delivery. The advantage is flexibility and gradualism. Civilization begins with minimal collectors and expands based on actual needs. Expansion pauses or accelerates based on priorities. Resources for construction don't prevent other activities. Civilizations can pursue multiple projects simultaneously. As demands grow, swarms expand naturally. Percentage capture reveals how much energy a civilization requires. Complete coverage captures 99% of radiation. 50% coverage provides abundant power for all purposes. Even 1% of a sun-like star exceeds human annual energy use 100 million times over. Partial Dyson structures provide energy beyond comprehension. Civilizations need small fractions of stellar output to support billions. Complete coverage might be pursued for strategy or simplicity. Early-stage construction focuses on capturing enough energy for further expansion. Energy needs depend on population, technology, and industrialization. Human civilization uses about 180,000 terawatts annually. Type 1 civilizations might use thousands to millions times more. Type 2 civilizations support trillions across orbital habitats. Energy needs grow with development. Advanced technology opens new applications. Computational systems require enormous power. Manufacturing operates at continental scales. Trillions need life support and lighting. Transportation spanning star systems needs propulsion energy. Stellar energy becomes necessary because civilizations grow beyond planetary capacity. Complete Dyson construction shows diminishing returns for most civilizations. Building final collectors to capture remaining energy requires disproportionate effort. resources serve better for expansion or technology development. Partial coverage already provides energy beyond earlier ages' dreams. Complete coverage becomes principle rather than necessity. Some pursue it for mastery, others remain content with partial coverage. The choice reflects cultural values. Expansion-focused civilizations build modest coverage, then colonize stars. Engineering-focused civilizations pursue complete coverage as achievement. Different civilizations interpret Dyson concepts differently. Material requirements require disassembly and processing of entire planets. A complete swarm at near-Earth distance requires roughly Jupiter's mass. Jupiter contains more material than all other planets combined. Processing involves breaking bodies, refining material, and constructing billions of spacecraft. Energy for processing would be enormous. Civilizations must harness stellar energy or develop power sources before major construction. First collectors provide energy for next-generation collectors. Mercury, smaller but closer, serves as material source. Material availability becomes the key limiting factor. Without sufficient material, even advanced civilizations cannot build complete swarms. Mining asteroids represents a modest approach compared to planetary disassembly. Solar systems contain billions of asteroids and comets. Mining distributes extraction across many bodies. Asteroid mining supports construction without destroying planets. The challenge is that asteroids are small and scattered. Each requires individual prospecting and mining. The process is slower than harvesting single planets. However, it preserves planets for habitats or biological reserves. Asteroid mining demonstrates less destructive approach while enabling construction. Mercury represents the most practical planetary option for Dyson material. It sits closest to the Sun at 0.39 AU. Proximity reduces transportation distances for inner collectors. Mercury is small, making disassembly more feasible than Jupiter or Earth. Civilizations systematically reduce it to atoms. Material processes into metals for construction. Some material remains near Mercury's orbit, while other material transports farther. Disassembly takes centuries or millennia. Mercury's proximity makes it efficient for stellar engineering. Using Mercury reduces mining operations. Material easily directs into solar orbit. Mercury emerges as prime candidate through trade-off analysis. It stays close to the Sun, minimizing transportation. It has substantial mass for construction. It is single-body, simplifying logistics. It contains useful elements. Destroying Mercury poses no habitability threat. Mercury's location makes it ideal for infrastructure. Material refines at the same location, avoiding transport. Venus and Earth have atmospheres worth preserving. Mars is farther, increasing costs. Outer planets are too distant. Mercury represents the practical optimum choice. Total solar system mass far exceeds needs for complete megastructure. The Sun dominates by mass, but swarms capture energy without consuming it. Planets contain roughly 5 times Jupiter's mass. Asteroids number billions. Comets extend farther with reserves. Civilizations have material choices without consuming the Sun. The star provides energy, making harvest worthwhile. Energy returned vastly exceeds processing costs. Surplus grows as collectors come online. civilizations bootstrap construction using earlier collector profits. Converting planets into infrastructure represents the ultimate endpoint of stellar engineering. Rather than viewing planets as preserved habitats or resources held in reserve, a civilization at Type 2 status might see them as construction material. The distinction between planet and infrastructure becomes philosophical rather than practical. A planet converted to orbital collectors still supports the civilization, but in a different form. Instead of surface dwellers, the population lives in habitats powered by collector infrastructure. Habitats could provide environments every bit as pleasant as planetary surfaces, while utilizing material far more efficiently. The atmosphere and biosphere could be preserved in contained habitats, rather than covering an entire planetary surface. Converting planets to infrastructure allows a civilization to scale to larger populations and greater industrial capability. A single planet converted to collectors might support 1 trillion inhabitants with absolute material abundance. Multiple planets converted over centuries could support population and civilization growth for geologic timescales. The conversion of planets to Dyson structures represents a path to civilization persistence and prosperity. Self-replicating machines accelerate the construction timeline dramatically by enabling exponential growth. A self-replicating spacecraft contains manufacturing systems capable of producing copies of itself using raw materials. The first machine mines asteroids, refines material, and builds a second machine. Both machines then work together to build 2 more. The population doubles repeatedly in exponential fashion. Within months, a small swarm of machines becomes a large swarm. Within years, the swarm can engage in major construction projects. Self-replicating machinery could transform asteroid material into Dyson components at exponential rates. The exponential growth eventually becomes limited by available material and energy constraints. A civilization deploying self-replicating machines could construct Dyson infrastructure vastly faster than traditional methods. The technology raises risks as well. A runaway replication process could consume all available material in a star system, if not carefully controlled. Containment protocols and resource limits would be essential. Despite risks, self-replication offers the most rapid path to megastructure completion. Von Neumann probes represent a specific type of self-replicating spacecraft designed for interstellar exploration. Named after mathematician John von Neumann, who developed the theory of self-reproducing machines, these probes would carry manufacturing systems enabling them to build copies of themselves. A von Neumann probe landing on an asteroid would mine material, refine it, and construct new probes. These probes would spread throughout the solar system, exploring and exploiting resources. The original probe could then venture to a nearby star, carrying knowledge and beginning expansion there. Von Neumann probes offer a strategy for expanding civilization across multiple star systems. In a Dyson context, these machines could rapidly build collectors across a large volume of space. A single von Neumann probe system deployed near a star could eventually fill the entire star system with collectors. The replication process requires safeguards against runaway expansion, consuming everything. However, with proper programming and oversight, the technology offers tremendous capability. Von Neumann probes also enable expansion to other stars without limiting civilization to a single system. Exponential growth in construction occurs when self-replicating systems work without constraints. Imagine starting with a single mining drone. It produces 2 drones. Those 2 produce 4. 4 produce 8. After just 30 doublings, you have over 1 billion drones. Exponential growth is slow at first, but becomes stupendously rapid very quickly. A swarm undergoing exponential growth can consume available resources in a star system within years or decades. The growth eventually hits hard limits when material or energy becomes scarce. A civilization managing exponential growth must carefully control the process to prevent consuming valuable resources or destabilizing the system. Exponential growth enables rapid Dyson construction, but requires careful oversight. The same exponential processes that build infrastructure could potentially cause environmental damage if mismanaged. A civilization mastering exponential manufacturing would gain tremendous capability, but assumes corresponding responsibility for restraint. Timeline estimates for building a complete Dyson swarm range from centuries to millennia, depending on starting conditions and growth strategies. A civilization beginning with current human technology might require thousands of years to complete a Dyson sphere around the Sun. A more advanced civilization might accomplish it in centuries. A civilization using self-replicating machines and exponential growth could potentially complete meaningful Dyson infrastructure within decades. The timeline depends on initial power availability, starting material abundance, technological capability, and population size. A civilization with small population and limited initial power would progress slowly. A civilization with large population and sophisticated technology could progress rapidly. Most realist estimates suggest a Type 2 Dyson sphere requires at least several centuries to construct. This timeline might seem impossibly long, but represents only a fraction of a star's lifetime. A Dyson structure, built today, would function for billions of years. The energy captured over that period vastly exceeds the construction investment. A civilization thinking in timescales of millions of years sees Dyson construction as a worthwhile long-term project. Energy needed to build the structure itself represents a substantial but not prohibitive requirement. Creating spacecraft, mining equipment, and processing facilities requires manufacturing. Moving material from planets to construction sites requires transportation energy. Refining raw material into usable metals and compounds requires processing energy. A civilization would need to produce some initial power source before beginning major construction. Once initial collectors come online, their energy output can fund further construction. The process becomes self-sustaining as each new collector generates more power supporting the next generation. This bootstrapping process reveals why early stages require the most careful planning. A civilization must gather sufficient material and energy to begin the process, but lacks the abundant power available later. Overcoming this bootstrap phase might require decades or centuries of preparation. Once past it, growth accelerates as cumulative energy output increases. The initial energy investment required is large but finite, well within the capability of a technological civilization. The bootstrap problem describes the difficulty of beginning Dyson construction without existing stellar energy infrastructure. A civilization cannot build a large collector without substantial energy and material, but they need collectors to obtain abundant stellar energy. This circularity must be broken somehow. The solution involves starting small. A civilization develops initial space infrastructure using planetary energy sources. They build small collectors and energy transmission systems using conventional power. These collectors provide supplementary energy supporting larger construction efforts. The early collectors might be modest by Dyson standards, capturing just kilograms of material and producing modest power. But even modest power exceeds planetary renewable sources when scaled up. As early collectors mature, their energy output enables construction of larger collectors. This creates a virtuous cycle where increasing energy availability supports faster expansion. Solving the bootstrap problem requires patience, planning, and sustained commitment over generations. A civilization must maintain focus on the project through decades without seeing full benefits. The first generations of a civilization pursuing Dyson construction would make sacrifices their descendants would repay many times over. Starting with current technology requires recognizing the enormous gaps between human capability and Type 2 civilization. Current humans barely approach space. We have no permanent presence beyond low Earth orbit. Our largest spacecraft weigh hundreds of tons. We lack any current capability to mine asteroids or planets. We cannot yet manufacture in space at scale. We have no self-replicating machinery. We cannot transmit power wirelessly across space. From current human position, Dyson spheres seem impossibly distant. However, the physics is understood. The engineering, while extraordinarily challenging, follows known principles. A humanity that maintained technological progress for 1,000 years might achieve modest Dyson capabilities. A humanity continuing advancement for 10,000 years could realistically construct partial stellar megastructures. The path from human civilization to Type 2 status would require sustained effort and focus, but appears physically possible. The first steps involve establishing permanent space infrastructure, developing asteroid mining, and building modular spacecraft factories. Each step builds on previous achievements, gradually expanding capability until Dyson construction becomes practical. Space-based manufacturing represents a crucial technology for Dyson construction. Building collectors in space rather than Earth reduces transportation costs and enables larger structure scales. A factory in orbit could process asteroid material directly into finished components. Zero gravity provides advantages for certain manufacturing processes. Materials solidify differently without gravity pulling them downward. Liquids form perfect spheres. Crystals grow in unusual patterns. These properties could be exploited for certain specialized components. The factory would operate continuously, powered by the first collectors coming online. Early output would be modest, creating perhaps one collector per month. As more collectors came online providing power, factory output would accelerate. Eventually, the factory could produce dozens of collectors per month. Establishing the first space factory requires bootstrapping from planetary production. Initial components would be launched from Earth or lunar surface. Once in space, they would be assembled into the first factory. This factory would then produce components for the next generation of factories and collectors. Space-based manufacturing creates the infrastructure enabling exponential Dyson growth. Zero-gravity assembly advantages make space construction preferable to Earth-based manufacturing. In weightless conditions, massive structures can be manipulated by small forces. A ton of material that would require heavy equipment on Earth can be positioned with gentle pushes in space. Large structures can be assembled in 3 dimensions without worrying about structural loads. Materials can be positioned precisely without gravity distorting alignment. Assembly processes move faster without fighting gravity. The advantages become more pronounced with larger structures. A collector several kilometers across would be incredibly difficult to assemble under gravity. In zero gravity, it becomes straightforward, just demanding patience and precision. Space-based assembly also enables modular construction. Components manufactured separately can be brought together and integrated into final assemblies. This modular approach works better in microgravity than on planetary surfaces. A civilization pursuing Dyson construction would quickly develop sophisticated zero-gravity manufacturing and assembly techniques. These would become defining characteristics of their civilization, as central to their culture as agriculture is to human society. The role of three-dimensional printing in space opens remarkable manufacturing possibilities. Additive manufacturing builds objects by depositing material layer by layer. This works as well or better in space than on Earth. A printer in orbit could manufacture complex parts from asteroid material transformed into usable feedstock. Multiple printers working in parallel could produce components at scales Earth-based factories could never match. Three-dimensional printing enables manufacturing of optimized structures impossible to create through traditional machining. Computer-designed structures can be printed directly without traditional tool requirements. This flexibility would accelerate Dyson construction dramatically. A civilization with advanced additive manufacturing could produce specialized components in enormous variety. Different collectors could be optimized for different orbital positions and purposes. The flexibility of additive manufacturing enables rapid design iteration and improvement. New designs could be tested quickly and refined based on performance data. Over decades of operation, collectors would improve through accumulated experience and innovation. Three-dimensional printing technology represents one of the most crucial capabilities for advanced space civilization. Transmitting energy back to users requires solving the challenge of wireless power delivery across space. Energy collected at orbital facilities must reach users on planetary surfaces or in distant habitats. Traditional cables cannot span the distances involved. Wireless power transmission must achieve high efficiency to make economic sense. Several technologies show promise. Microwave beaming concentrates electromagnetic energy into directed beams. Laser transmission uses focused light to transmit power. Both require ground stations to receive and convert the transmitted energy back into electrical form. Microwave transmission penetrates clouds, while laser transmission requires clear line of sight. Both face efficiency losses to atmosphere and diffusion. Efficiency improves with higher frequencies and larger receiver areas. A receiving station the size of a small city could collect enormous power from distant transmitters. Wireless transmission enables distribution of power throughout a civilization despite vast distances. Rather than feeding specific cities or installations, transmitters could serve distributed recipients across a star system. Microwave power beaming uses electromagnetic radiation at microwave frequencies to transmit energy across space. Microwave frequencies penetrate Earth's atmosphere reasonably well, while remaining safe for biological systems at moderate intensities. A transmitter in space could focus microwave energy into a beam directed toward a ground receiver. The receiver would be a large antenna array called a rectenna, capable of converting electromagnetic energy into electrical current. Microwave transmission works at any distance that line of sight is maintained. Efficiency improves with larger transmitter and receiver apertures. A transmitter measuring kilometers across could beam power to a receiver hundreds of kilometers away with reasonable efficiency. The technology has been demonstrated at small scales and appears scalable to larger systems. Microwave beaming could be the primary method for distributing Dyson energy throughout a civilization. Different transmitters could beam to different receivers, creating networks distributing power where needed. The flexibility allows customizing energy distribution to match civilization needs. Ground stations receiving microwave power could then distribute it locally through conventional electrical grids. Laser power transmission uses focused light beams to transmit power across space. Lasers concentrate light into coherent beams that maintain focus over vast distances. A high-powered laser in space could beam energy to a ground receiver kilometers away. The receiver would be a solar panel array optimized for the laser wavelength. Laser transmission offers higher efficiency than microwave for the same transmitted power. Laser beams are narrower and more focused than microwave. Light carries more energy per unit area than microwaves at the same transmission distance. However, lasers require clear line of sight. Clouds block laser beams while microwave penetrates clouds. A civilization would likely use both microwave and laser transmission depending on circumstances. Lasers could transmit to receivers in space or to clear sky ground stations. Microwave could serve users in cloudy regions. The flexibility of multiple transmission modes ensures reliable power distribution regardless of weather or location. Laser transmission also enables beaming power to moving targets like spacecraft. A spacecraft could maintain power connection by receiving a directed laser beam during transit. The efficiency of wireless power transmission depends on multiple factors including transmitter size, receiver size, distance, and frequency. Larger transmitters and receivers improve efficiency. Higher frequencies allow focusing into narrower beams, reducing spreading loss. Greater distances increase beam diffusion, unless apertures are very large. Theoretical analysis suggests wireless power transmission could achieve 70 to 90% efficiency for well-designed systems. Practical systems would probably achieve 50 to 80% efficiency, accounting for atmospheric losses, conversion inefficiencies, and geometric factors. These efficiency levels make wireless transmission competitive with traditional wired distribution across space-scale distances. The energy losses convert to heat in the atmosphere or are scattered to space. Civilization would need to manage heating effects on the atmosphere from energy transmission. Massive power transmission might warm the atmosphere regionally. This constraint might require transmitting power through space rather than through atmosphere to avoid environmental effects. Efficiency and environmental impact both influence how civilization distributes energy from Dyson collectors. Safety concerns with directed energy beams primarily involve accidental exposure and deliberate weaponization. A high-powered microwave or laser beam carries enough energy to cause damage if striking unexpected targets. Proper targeting systems and safeguards would prevent accidental exposure. Birds or aircraft straying into beams could be damaged. Stringent protocols would need to control airspace around receiving stations. A civilization with advanced directed energy capability possesses devastating weapons. A laser powerful enough to transmit power could damage or destroy spacecraft and installations. Societies would need to establish agreements preventing weaponization of power transmission systems. International law would likely govern power transmission much as nuclear weapons are governed. The stakes are high enough that civilization stability could depend on effective treaties preventing energy weapon development. Technical verification systems would monitor power transmission to confirm compliance. The safety and security challenges are surmountable, but require careful governance and cooperation. Receiving stations and rectenna arrays are the destinations for wireless power transmission. A rectenna is a large antenna array with integrated rectifier circuits converting electromagnetic energy into direct current. Rectenna arrays could measure kilometers across to collect transmitted energy efficiently. The direct current from rectennas feeds into power management systems distributing electricity locally. Ground-based rectennas would be located in regions receiving regular microwave or laser transmission. Multiple rectennas could receive from multiple transmitters, creating redundancy. If one transmission path failed, others could compensate, maintaining power supply. This distributed receiving system proves more robust than concentrated power plants. Rectenna technology requires advanced emment from current capabilities but follows well-understood principles. Superconducting elements could minimize losses. Phased array techniques could optimize reception. A network of rectennas distributed globally could receive and distribute power from Dyson collectors to users everywhere. The receiver infrastructure represents as large an engineering undertaking as the collectors themselves, but appears entirely feasible. Where the energy might be used depends on civilization structure and priorities. A civilization with abundant power could support far larger population in far greater comfort. Life support systems for habitats could operate without constraint. Transportation throughout the star system becomes affordable when energy is abundant. Industrial manufacturing could operate at vast scales. Scientific research could pursue energy-intensive experiments. Space exploration and expansion accelerates with abundant energy. Different civilizations would apply energy differently based on values and priorities. Some might emphasize comfort and abundance. Others might focus on exploration and expansion. Still others might pursue art and culture enabled by transcending resource constraints. The abundance from Dyson structures enables civilizations to transcend material scarcity that has constrained human history. The resulting transformation in civilization character could be profound, enabling societies unimaginable to current humans. Planetary surface applications of Dyson energy would keep habitable planets functional despite proximity to such intensive infrastructure. Even if Dyson collectors surrounded a star, selected planets could retain habitable surfaces receiving designated power from collectors. Energy could run planetary life support systems, maintain atmospheric composition, and provide comfortable conditions. A planet could be transformed into a garden world optimized for life. Elaborate ecosystems could be cultivated. Biodiversity could be maximized. The planet becomes a carefully managed biological reserve rather than a natural system. Alternative applications could transform planetary surfaces into industrial or residential complexes. Cities covering entire continents would be possible with abundant power, and advanced technology. Underground facilities and domed habitats could create entirely new environment types. A civilization could utilize planetary surfaces in diverse ways, each supported by Dyson energy transmission. Space habitats powered by the swarm would be the most common form of population settlement. Habitats built in free space would require continuous power for life support. Dyson collectors could transmit power to habitats throughout the star system. Habitats could be positioned at any location in orbital space. Some might cluster near planets. Others might be scattered throughout the system. Each habitat would receive power from nearby collectors or through transmitted power from distant collectors. The abundance of energy would allow construction of enormous habitats supporting millions or billions of inhabitants. Habitats could recreate natural environments through artificial means. Rotating habitats could create simulated gravity. Comprehensive recycling systems would maintain resources indefinitely. A civilization living in space habitats supplied by Dyson collectors could number in the trillions. Such a civilization would truly be Type 2, controlling stellar energy for the benefit of its enormous population. Industrial applications of Dyson energy enable manufacturing and processing on continental scales. Chemical processing, metal refining, semiconductor production, and countless other industries require energy. With abundance from Dyson collectors, these industries could expand vastly. Factories could operate continuously producing goods for the enormous population. Raw materials from asteroids could be processed into finished products. Construction of new space habitats would be rapid with abundant industrial capacity. New collectors and infrastructure could be manufactured at unprecedented rates. Industrial civilization at Type 2 level would likely focus on construction of habitats and infrastructure as primary economic activity. The civilization would be engaged in perpetual expansion and development, creating new structures throughout the star system. Manufacturing would be the dominant activity, with agriculture and other primary industries minimized through efficiency. A civilization with such capacity would reshape its entire star system according to intentional design. Terraforming other worlds using abundant Dyson energy becomes practical and economical. Worlds unsuitable for life could be modified to support biospheres. Atmosphere could be built on airless worlds. Planetary temperatures could be regulated through energy input. Magnetic fields could be generated to protect against solar wind. Given centuries of effort and abundant energy, any rocky world could become habitable. Outer planets could be warmed, allowing life to emerge. A civilization could transform its entire star system into habitable spaces. Hundreds or thousands of habitable worlds could exist where previously only one or two did. Population limits would be imposed only by raw material availability rather than energy constraints. Terraforming at Type 2 scale would create an entirely repropulse figure. A point which of this tidal light would create an entirely repropulse figure made solar system reflecting intentional design and purpose. Such projects would dwarf any earthly engineering accomplishment and would take centuries but appear feasible with Type 2 capability. Propelling interstellar spacecraft using Dyson power enables expansion to neighboring stars. Space travel requires enormous energy, particularly to reach relativistic velocities necessary for interstellar journeys. A civilization with abundant Dyson energy could build spacecraft accelerated to near light speed. Laser or microwave beams could push sails on spacecraft through their journey. A civilization would be freed from confinement to a single star system. Expansion could proceed to nearby stars within centuries. Multiple star systems could be colonized and developed. Multiple Dyson structures built around different stars could form a civilization spanning light years. A civilization reaching Type 3 status would be engaged in systematic colonization of entire galactic regions. The catalyst enabling such expansion would be development of Type 2 Dyson structures, providing abundant energy for interstellar travel. Dyson spheres thus represent not only stellar engineering achievement, but foundation for galactic civilization. The computational uses of mega-energy exceed our current imagination. A civilization with stellar-scale energy could power computational systems far beyond current capability. Artificial intelligences could be developed running on vast numbers of processors consuming gigawatts of power. Such intelligences could engage in complex modeling, simulation, and analysis. Scientific research could be pursued at scales currently impossible. The universe could be simulated in vast detail, enabling understanding of physics and chemistry. Weather and climate systems could be precisely modeled. Biological processes could be simulated at molecular level. The civilization could create vast virtual worlds simulating alternate scenarios. Computation might become the dominant use of Dyson energy as civilization evolved. A civilization using stellar energy primarily for computation would be engaged in understanding and exploring their universe at depths impossible for current humans. The very nature of reality could be investigated through simulation and theoretical modeling powered by Dyson structures. The remarkable flexibility of stellar energy application reveals why advanced civilizations would pursue Dyson construction relentlessly. Yet beneath this grand vision lies a constellation of challenges testing any civilization. Imagine constructing billions of satellites orbiting at different velocities and distances. The complexity compounds exponentially as the number of objects increases. Even a handful of spacecraft require careful coordination. A complete Dyson structure demands orchestration surpassing contemporary human capability by orders of magnitude. The practical obstacles are fundamental barriers requiring novel solutions. Civilization would need to develop technologies that do not yet exist. The challenges reveal why Dyson spheres remain theoretical rather than realized. Understanding these obstacles clarifies why Type 2 civilizations remain elusive despite our searches. Orbital debris represents the most immediate practical challenge facing any civilization attempting Dyson construction. In Earth orbit today, millions of pieces of debris from defunct satellites circle the planet at velocities exceeding 20 kilometers per second. Even tiny fragments traveling at such speeds carry kinetic energy capable of destroying functioning spacecraft. A piece of paint can pierce a pressurized module. The debris environment near Earth demonstrates how quickly objects accumulate and become dangerous. Expanding this problem to a star system scale reveals terrifying implications. A complete Dyson swarm would contain billions of active collectors, plus potentially trillions of debris fragments. A single major collision could generate cascading debris, creating more ions in exponential fashion. A runaway cascade could render entire orbital regions unusable. Managing debris would require constant monitoring and active removal operations. Collision risks intensify as swarm density increases toward full coverage. The probability that two random objects will collide rises dramatically as the number of objects grows. With millions of collectors occupying the space near a star, the collision probability becomes significant. Each collision generates debris that increases subsequent collision risk. Objects at different orbital altitudes and velocities follow complex intersecting paths. Calculating safe trajectories requires computational sophistication. Sophisticated collision avoidance systems would be essential, monitoring positions constantly and adjusting trajectories. Advanced civilization would implement redundant safety systems. Automated systems would respond faster than biological organisms. Even so, the sheer number of objects creates inherent risk. Some collisions might prove inevitable, despite precautions. Managing acceptable collision rates would require continuous vigilance. Traffic control at stellar scales represents a problem qualitatively different from Earth orbital management. Air traffic control manages thousands of aircraft. Dyson swarm traffic control would manage billions or trillions of objects. The computational burden exceeds contemporary capacity by trillions of times. Each object must know its position, velocity, and planned trajectory. Communication systems must transmit positional updates continuously. A civilization would require dedicated computational infrastructure. Artificial intelligences spanning planetary masses would coordinate constantly. The system would predict trajectories, identify potential collisions, and issue corrections. Despite the vast resources devoted to traffic control, occasional collisions would occur. A civilization would accept these risks as inevitable costs. Communication delays across a star system create fundamental coordination problems. Light travels at finite velocity, covering the distance from Earth to the Sun in 8 minutes. For collectors orbiting farther from the star, communication delays would be proportionally longer. An object at 10 times Earth's distance experiences 80-minute communication delays. Instructions would require hours to reach distant collectors. During communication delay periods, events might develop without immediate correction. Distributed autonomous systems would be necessary. Individual collectors would make local decisions without waiting for central guidance. This distribution of authority creates coordination challenges. Different collectors might make conflicting decisions. Standardized protocols would govern behavior without requiring centralized control. The system would function despite inherent communication delays. Speed of light limitations represent a fundamental constraint that cannot be overcome through engineering. A Dyson sphere cannot respond faster to disturbances than light allows. Information cannot travel faster than light through the vacuum. This immutable law becomes a practical limitation. Controlling billions of objects becomes impossible with perfect precision. The civilization would accept error margins and occasional failures. Some degree of autonomous operation becomes necessary. Decision-making authority must be distributed throughout the swarm. Individual collectors must respond to local conditions without waiting for distant instructions. This creates risks of coordination failures. Different collectors might occasionally make incompatible decisions. The civilization would optimize protocols to minimize conflicts while accepting that complete coordination remains impossible. No amount of technological advancement can overcome this fundamental limitation. Understanding this constraint clarifies why perfect control cannot exist. Coordinating billions of collectors requires developing entirely new system architectures. Current distributed systems manage millions of computers. A Dyson swarm would require managing trillions of objects. The increase in complexity is exponential, requiring novel approaches. Civilization would need artificial intelligence systems spanning continental or planetary masses. These intelligences would exist as distributed networks without central processing locations. Information would flow constantly throughout the network, updating positions and status. The system would self-organize and adapt to changing conditions. If one collector failed, others would compensate. If communications failed, local systems would continue operating autonomously. The system would be robust against partial failures while remaining globally coordinated. Building such systems would require centuries of research and development. Trial and error would reveal optimal approaches. Civilization would gradually develop the expertise necessary to manage planetary-scale distributed systems. Distributed versus centralized control strategies present fundamental trade-offs that civilization must resolve. Centralized control offers simplicity and coordination, but requires fast communication across the entire star system. Distributed control enables autonomous operation, but risks coordination failures. A hybrid approach would likely emerge, combining centralized oversight with distributed autonomous decision-making. Higher-level decisions about energy distribution and expansion would remain centralized. Tactical decisions about collision avoidance and local operations would be distributed. Different types of decisions would follow different governance structures optimized for their particular requirements. Some redundancy would exist with multiple authority structures capable of commanding the swarm. If primary control structures failed, backup systems would assume control. The civilization would design the control architecture with extraordinary care to prevent catastrophic failures. Testing the system during construction would reveal flaws before deploying the full swarm. Gradually expanding operations would allow civilizations to identify problems and correct them iteratively. The balance between centralization and distribution would shift over time based on experience. Eventually, civilization would achieve elegant solutions that appear simple but represent centuries of refinement. Failure modes and redundancy concerns become increasingly critical as the swarm grows larger. Complex systems invariably experience failures. Civilization must design the swarm to tolerate failures gracefully. If a collector fails, others must compensate. If a control system fails, backups must assume its functions. Multiple independent power transmission systems would ensure energy flows despite individual failures. Redundant collectors would be positioned throughout the swarm, providing backup capacity. Critical functions would have multiple independent implementations. Civilization would build excess capacity intentionally. This excess becomes essential for reliability. The swarm cannot fail without catastrophic consequences. Civilization would gladly sacrifice efficiency to ensure reliability. The engineering of failure tolerance becomes as important as energy collection. When collectors inevitably break down, replacement and repair operations must continue indefinitely. A Dyson swarm operating for billions of years will experience enormous numbers of failures. Each failed collector must be replaced or repaired. The civilization must maintain continuous manufacturing capacity to produce replacement collectors. The energy invested in manufacturing replacements must be small compared to the energy collected. This requires manufacturing efficiency improving over time. Early collectors might require 1,000 hours of manufacturing energy per unit of collected energy over their lifetime. Advanced collectors might achieve ratios approaching unity or even less. Civilization would focus on increasing manufacturing efficiency as a priority. Robots and autonomous systems would dominate manufacturing and repair operations. The workforce would be entirely mechanical rather than biological. Biological inhabitants would focus on higher-level management and planning. Manufacturing would operate continuously, requiring no rest or downtime. A civilization would develop manufacturing sophistication matching the sophistication of collection systems. Repair and replacement would become routine operations hardly worthy of attention. The continuous replacement of aging collectors would be fundamental to civilization's operation. Like cellular replacement in biological organisms, maintenance at astronomical scale requires developing remote operation capabilities beyond current human experience. Traveling to distant locations around the sun takes months or years. Maintenance workers cannot respond quickly to problems. Remote robotic systems must handle most repairs. Technicians would diagnose problems through remote sensors and command robots to perform repairs. Civilization would develop a network of remote maintenance facilities positioned throughout the swarm. These facilities would house repair equipment and spare parts. Technicians would rotate through duty stations on years-long assignments. The maintenance infrastructure would rival the collection infrastructure in scale. Civilization would develop expertise in remote operation that exceeds contemporary understanding. The challenges would drive innovation in robotics and automation. Repair robots and autonomous systems must achieve sophistication, allowing them to handle unpredictable failures. Failures rarely follow predictable patterns. Robots must diagnose problems and determine solutions without waiting for distant instructions. Machine learning systems would analyze telemetry from millions of collectors, identifying imminent failures. Preventive repairs would address problems before they become critical. Robots would learn from each repair operation, improving their capabilities. Over time, autonomous systems would become increasingly sophisticated. Robots would self-diagnose and self-repair when possible. The civilization would cultivate ecosystems of autonomous systems, continuously improving. Some robots would specialize in common repairs. Others would handle specialized failures. The system would evolve toward greater autonomy and reliability. Eventually, the swarm would be largely self-maintaining. The robots would represent civilization's greatest achievements. Stellar variability presents challenges to the swarm that cannot be controlled or predicted. The Sun and other stars are not constant sources of radiation. Solar activity cycles over periods of years or decades. Solar flares can suddenly increase radiation output. Sunspot activity varies, affecting total radiation output. A collector designed for average output might be overwhelmed during peak activity periods. Radiation might damage components if protective systems fail. Energy transmission systems might receive unexpected surges of energy. The swarm must accommodate these variations without damage. Collectors would need protection against excessive radiation. Surge protection systems would prevent damage during peaks. Some collectors might be designed specifically to handle high radiation conditions. Civilization would study the target star extensively before building collectors, optimizing designs for expected variability. Long-term climate observations would reveal patterns, allowing prediction of future activity. The swarm would adapt dynamically as civilization learns more about the star's behavior. Understanding stellar variability would be as important as understanding engineering principles. Astronomy and engineering would combine in pursuit of safe Dyson operation. Solar flares and radiation storms create acute hazards that could damage the swarm severely. A powerful solar flare can release enormous energy in short periods. The radiation shower following a flare can strike collectors unexpectedly. Sensitive electronics might be damaged by radiation exposure. Solar panels might lose efficiency from radiation damage. Crews would experience dangerous radiation levels. A severe storm might cause casualties among maintenance personnel. Collectors would need radiation shielding protecting vital components. Electronics would use radiation-hardened versions operating reliably despite radiation exposure. Spare shielding would be carried aboard collectors, allowing repairs. Early warning systems would detect solar activity and trigger protective actions. When a flare was detected, collectors would adjust positions to minimize exposure. Radiation-sensitive operations would pause until the storm passed. Crews would shelter in heavily shielded locations. The civilization would develop protocols and systems minimizing flare damage. Despite precautions, occasional damage would occur. Civilization would accept this as an inevitable cost of stellar proximity. The energy benefits would far exceed the costs of occasional storm damage. Protecting collectors from damage requires developing materials and designs resilient against multiple hazards. Radiation presents one hazard. Micrometeorite impacts represent another. Heat dissipation challenges arise from solar proximity. Thermal stress can damage structures. Ultraviolet radiation degrades materials. Vibration from solar wind can cause fatigue. Collectors must withstand multiple simultaneous stresses. Materials would be selected for resilience. Design would emphasize robustness over minimal mass. Some redundancy would be intentional. Collectors would be designed for easy replacement. Preventive maintenance would address minor damage. Civilization would develop materials optimized for stellar environment operation. Each generation would be more resilient than previous science. The collectors would represent engineering achievement in materials science. Radiation hardening of components ensures electronics function despite high radiation exposure. Integrated circuits can be damaged by radiation. Radiation-hardened circuits use special design techniques. Redundant circuits allow voting systems identifying errors. Error-correcting codes detect and correct errors automatically. Space-qualified electronics already use hardening techniques. Dyson collectors would use these extensively. Additional shielding would protect critical systems. Collectors would operate slower because hardened components run slower. This trade-off would be accepted without hesitation. Civilization would prefer slow, reliable collectors. The cost of hardening would be trivial compared to replacement. Virtually all components would be radiation-hardened designs. The solar wind's impact on collectors represents a persistent challenge requiring ongoing attention. Solar wind carries charged particles streaming outward from the sun. These particles exert pressure on objects. The pressure is subtle but continuous. Over time, accumulated pressure can alter orbits. Collectors must adjust positions to maintain orbits against solar wind pressure. This requires continuous fuel consumption. Some collectors might use solar wind pressure purposefully. Sails could catch solar wind pressure providing propulsion. By adjusting sail angle, collectors could ride the solar wind. This would eliminate fuel requirements for some maneuvers. Other collectors would use ion engines. The choice depends on mission requirements. The civilization would optimize each collector for its particular role. The cumulative propulsion requirements would be manageable with proper planning. Magnetic field interactions present subtle but important effects on the swarm. Stars generate magnetic fields that extend throughout their planetary systems. Collectors carrying electrical currents interact with magnetic fields experiencing forces. These forces could push collectors off intended trajectories. The civilization would account for magnetic effects when designing orbits. Shields could protect sensitive systems. Collectors might exploit magnetic fields for propulsion. The magnetic environment would be mapped extensively before building the full swarm. Precise knowledge would enable optimization. As the civilization learned about magnetic behavior, models would improve. The swarm would adapt over time. Interaction would be inevitable, but manageable with proper engineering. Searching for Dyson spheres in the sky represents a major observational program seeking signatures of advanced civilization. Astronomers have conducted surveys looking for unusual infrared signatures suggesting artificial structures. The searches assume civilizations would produce detectable infrared waste heat. Large-scale infrared surveys examine millions of stars for anomalies. Unusual infrared to visible light ratios suggest possible Dyson structures. Several research programs have examined infrared source catalogs comparing them against expected natural phenomena. No confirmed Dyson spheres have been found despite careful examination. The absence does not prove they do not exist. They might be rare, distant, or hidden. The searches continue with improving sensitivity. Better telescopes improve detection capabilities. New analysis techniques improve discrimination between artificial and natural phenomena. Infrared excess as a signature stems from thermodynamic principles governing energy transformation. A star naturally emits visible light, representing its photosphere temperature. Matter surrounding the star absorbs visible light and emits infrared waste heat. The infrared excess represents energy captured and re-emitted at longer wavelengths. Comparing observed infrared emission to expected levels for the star's type reveals excess. An object completely surrounding a star would produce strong infrared excess. Partial Dyson structures would produce weaker excess. The excess would be proportional to the coverage fraction and the efficiency of conversion. A civilization building a half-coverage Dyson swarm operating at 50% efficiency would show infrared excess roughly 25% above background. The excess would be concentrated in the thermal infrared region around 10 micrometers. Observers would see unusual spectral profiles with strong emission at these wavelengths. The infrared excess signature is theoretically robust and should be detectable if Dyson spheres exist in observable regions of the galaxy. What astronomers specifically look for in surveys involves detailed spectral analysis and comparison procedures. Infrared catalogs list thousands of sources with measured brightness at multiple wavelengths. Researchers extract sources showing unusual infrared to visible ratios. The ratios are compared against predictions for common astronomical objects. Stars show expected ratios based on their temperature. Galaxies show characteristic ratios based on dust content. Asteroids and dust clouds show their own distinctive ratios. Sources that do not match any known category become candidates for further investigation. Candidates undergo additional scrutiny, examining color information and positional data. Some candidates might be new classes of objects rather than Dyson spheres. Distinguishing Dyson signatures from other phenomena remains challenging. Most candidates are eventually explained as unusual natural phenomena. The handful remaining unexplained continue to receive attention. Advanced analysis techniques continue improving discrimination ability. Multi-wavelength observations provide more information, enabling better classification. The search continues, systematically examining the entire infrared sky. The temperature profile of waste heat provides signatures distinguishing Dyson spheres from other phenomena. A natural star surrounded by dust shows temperature gradients. Inner dust is hot from proximity to the star. Outer dust is cool from distance. A Dyson swarm shows different structure. Collectors could operate at similar temperatures if designed that way. Alternatively, they might show discrete clustering at specific orbital distances. The temperature profile would be unusual compared to natural dust distributions. Analysis of spectral features could reveal whether heat sources are distributed continuously or concentrated at specific locations. Observations at multiple wavelengths would map the temperature distribution. Distinguishing signatures would require detailed observations and careful analysis. Distinguishing Dyson signatures from natural phenomena remains one of the primary technical challenges in detection programs. Many astronomical phenomena produce infrared excess. Nearby dust clouds around young stars show strong infrared from warm dust. Evolved stars undergoing mass loss produce dusty envelopes. Active galaxies harbor massive dust reservoirs. Binary systems with accretion disks produce infrared radiation. Each phenomena has characteristic spectral signatures helping distinguish it from others. Dyson spheres would show signatures distinct from these common objects. However, some resemblance to natural phenomena is inevitable. Careful analysis comparing observations to models would reveal inconsistencies. An object matching all characteristics of a Dyson sphere while being explainable as natural phenomena would be reported as probable natural phenomena. The evidence for artificial origin would need to be compelling. Multiple independent signatures, all suggesting artificial nature, would be required. A single unusual characteristic could result from unfamiliar natural phenomena. The bar for claiming discovery would be high, requiring overwhelming evidence. Dust clouds and protoplanetary disks show infrared characteristics superficially similar to Dyson signatures. Young stellar systems are surrounded by material from star formation. These disks contain warm dust-producing infrared radiation. The infrared excess from young stars can exceed that of mature stars by orders of magnitude. Young stars have specific characteristics, including associated visible star formation. Disk morphology can be mapped, revealing characteristic structures. Young disks show temperature gradients from warm inner regions to cool outer regions. Dyson spheres would show different structural characteristics. Spectroscopic analysis would show different chemical compositions. Young disks contain silicate minerals showing characteristic features. Dyson structures would produce featureless infrared spectra. Advanced observations would distinguish these phenomena readily. The limits of current detection technology constrain our ability to discover distant Dyson spheres. Infrared telescopes observe in specific bands lacking complete coverage. Space observatories observe selected regions rather than entire sky simultaneously. Sensitivity limits prevent detecting weak infrared excess from distant objects. Dust in the galactic plane obscures infrared observations in many directions. A very distant Dyson sphere would be faint beyond detection capability. A nearby sphere with low thermal output might remain hidden. Current capabilities would discover only prominent nearby Dyson spheres. The majority of Dyson spheres, if they exist, could remain undetected. Future improvements in observational capability would extend detection range. Planned infrared missions will survey larger regions with greater sensitivity. Improved analysis techniques will better distinguish signatures. Decades of effort will be required to comprehensively survey the galaxy. The absence of detections to date reflects either genuine rarity of Dyson spheres or our limited detection capability. Only continued systematic searching will resolve this fundamental question. Survey projects and searches continue, despite the absence of confirmed detections. The infrared astronomical satellite missions have produced catalogues of millions of sources. Researchers have examined these catalogues looking for Dyson candidates. Statistical analyses identify sources with unusual properties. Targeted observations of candidates provide additional information. The searches have refined techniques for identifying promising candidates. Several stars have been examined in detail, finding no conclusive evidence of Dyson structures. Nevertheless, the searches continue because the potential discovery remains profound. A confirmed Dyson sphere would be the greatest astronomical discovery imaginable. Civilization would know definitively that advanced intelligence exists elsewhere. The philosophical and scientific implications would be staggering. The effort required to search thoroughly is trivial compared to the magnitude of potential discovery. Scientific motivation drives continued searching despite lack of positive results. The searches will continue for decades at minimum regardless of results. Tabby's star and the megastructure hypothesis captured public and scientific imagination, despite skeptical reception. In 2015, astronomers reported unusual dimming observations of a star designated KIC 8462852. The star showed episodic dips in brightness, unlike typical stellar variation. Some dips reduced brightness by 20% or more. The dips were irregular in timing and magnitude. The unusual behavior sparked speculation about possible megastructures. A megastructure around the star could block starlight, creating dimming. Dyson spheres during construction could produce exactly this behavior. The hypothesis captured headlines and public attention. Scientists acknowledged the megastructure possibility, while noting many alternative explanations existed. The unusual dimming could result from unknown natural phenomena, like swarms of comets. Subsequent observations provided additional data constraining possible explanations. The megastructure hypothesis became one among many competing theories. The uncertainty highlighted how genuinely exotic astronomical phenomena could mimic artificial signatures. Why unusual dimming caught attention relates to the departure from expected stellar behavior. Stars vary in brightness for well-understood reasons. Binary stars show periodic dimming as they eclipse each other. Pulsating stars show regular brightness oscillations. Star spots cause gradual dimming similar to sunspot effects. The dimming pattern of Tabby's star did not match these common phenomena. The pattern showed no periodicity. The magnitude of dimming was unusually large. Multiple dimming events scattered over time created a puzzle. Astronomers searched catalogues for similar stars, finding no other examples so unusual. The rarity of the phenomenon warranted serious investigation. The possibility of megastructure construction seemed worth considering, despite being speculative. The public interpreted the observations as suggesting alien engineering. Scientists urged caution about jumping to extraordinary conclusions. The incident demonstrated how unusual observations can generate intense interest and speculation. Natural explanations that emerged as more data accumulated provided mundane accounts for the observations. Dust from cometary bodies in the system could produce dimming. Unbound dust from stellar collisions could create temporary dimming. Hierarchical dust clouds could produce the observed irregular pattern. Theoretical modeling showed that various dust configurations could reproduce observations. The models accounted for the unusual characteristics without requiring exotic phenomena. The simplicity principle favored dust explanations over megastructure construction. Occam's razor suggested accepting dust explanations requiring no artificial structures. Additional infrared observations constraining dust properties became consistent with modest dust quantities. The infrared excess from the star did not match Dyson sphere predictions. The absence of characteristic infrared signatures argued against megastructure construction. The scientific consensus gradually shifted toward natural explanations. Tabby's star remained peculiar but ceased being candidate Dyson sphere. The experience highlighted how careful analysis eventually reveals natural explanations for initially mysterious phenomena. What we learned about detection from the Tabby's star episode clarified scientific requirements for megastructure identification. A single anomalous observation cannot prove megastructure existence. Multiple independent signatures, all pointing toward artificial origins, would be required. Infrared characteristics would need to match megastructure predictions, not natural phenomena. Spectroscopic features would need to exclude conventional explanations. The combination of unusual observations with detection of characteristic artificial signatures would be needed. A star showing infrared excess, unusual dimming, spectroscopic anomalies, and temporal patterns consistent only with megastructure construction would be compelling evidence. Single anomalies are insufficient regardless of how unusual. The requirement for multiple independent signatures sets a high bar for discovery. This stringent requirement reflects appropriate scientific skepticism. Extraordinary claims require extraordinary evidence. The search for Dyson spheres would require discoveries meeting the highest scientific standards. Other candidate stars occasionally attract attention for possible megastructure signatures. Several stars show unusually high infrared to visible ratios. Some demonstrate dimming patterns unusual compared to typical stellar behavior. However, alternative natural explanations exist for each candidate. None have reached the threshold where megastructure construction is the most plausible explanation. Scientists continue examining candidates carefully. Improved observations provide constraining data. Most candidates remain ambiguous without definitive conclusion. A few have been eliminated as natural phenomena became clear. The search remains open to new discoveries. The scientific community remains alert for signatures suggesting artificial construction. Statistical likelihood of discovery depends on actual prevalence of Dyson spheres in the galaxy. If Dyson spheres are common, discovery should occur within decades with current technology. If they are rare, detection might require centuries despite improved methods. If they are virtually non-existent, no amount of searching will find them. Current estimates vary wildly, reflecting genuine uncertainty. Some scientists argue that advanced civilizations would inevitably build Dyson structures, making them common. Others counter that megastructure construction is so demanding that few civilizations succeed. The truth likely lies somewhere between extremes. Perhaps 1% of suitable stars host Dyson spheres, perhaps 1 in 10 million, perhaps none. The actual prevalence remains unknown. Statistical analysis of survey results will eventually place constraints on prevalence. If surveys examine millions of stars finding zero candidates despite sensitivity to megastructures, prevalence must be extremely low. Continued negative results would imply Dyson spheres are rarer than many expected. The survey results will inform philosophical questions about civilization, prevalence, and technological paths. The vastness of space provides both opportunity and limitation for discovery searches. The observable universe contains roughly 2 trillion galaxies, each containing billions or trillions of stars. the total number of stars exceeds 10 to the 24th power. Dyson spheres could be hidden among this enormous population. Complete examination of all stars remains physically impossible. Telescopes can observe a tiny fraction of the sky at any time. Surveys observe sample regions, then extrapolate results to the whole sky. Statistical sampling allows inference about total populations from partial observation. A comprehensive infrared survey examining 10% of the sky provides reasonable statistics about the full population. Such surveys would be achievable within decades. The combination of sky coverage and sensitivity would constrain prevalence of megastructures. The results would be scientifically meaningful even without positive detection. The vastness of space means that discovery remains possible while remaining uncertain. The probability of success increases as survey capability improves. Why advanced civilizations might be rare relates to the difficulty of reaching technological sophistication necessary for megastructure construction. Civilizations must survive internal conflict, avoiding self-destruction. They must navigate environmental challenges without catastrophe. They must maintain progress for centuries without regression. They must avoid catastrophic mistakes leading to collapse. Every step toward advanced technology creates new dangers. Nuclear weapons, artificial intelligence, nanotechnology, and other powers pose existential risks. A civilization must thread an extremely narrow path. The probability of reaching Type 2 status remains uncertain and possibly small. Perhaps 99% of civilizations self-destruct before reaching megastructure capability. The handful surviving might be so scattered that overlap in time and space becomes unlikely. A civilization existing today might emerge too late to find others. Others might have existed billions of years in the past when the galaxy was younger. The timing of civilization emergence might prevent interaction and detection. Rarity could result not from civilizations choosing different technological paths, but from the difficulty of surviving to advanced stages. The Fermi paradox connection clarifies why Dyson sphere searches relate to fundamental questions about civilization presence. The Fermi paradox asks why we observe no evidence of extraterrestrial civilizations despite the apparent probability of their existence. The galaxy should harbor numerous advanced civilizations if intelligence commonly arises. Yet we detect no signals, no visits, no megastructures. The absence of evidence demands explanation. One possibility is that civilizations are genuinely rare. Another is that they choose not to expand or communicate. Dyson spheres would be detectable evidence of advanced civilization. A comprehensive search finding no Dyson spheres supports the rarity hypothesis. If searches confirmed Dyson sphere absence even in nearby stars, rarity becomes more probable. The searches thus address the Fermi paradox through negative results. An absence of Dyson spheres helps answer the profound question of civilization prevalence. If Dyson spheres are common, where they represent the most direct application of Fermi logic to megastructure searches. The reasoning is straightforward. If Dyson spheres are common, many should exist nearby. Nearby megastructures should be easily detectable. Their absence suggests they are not common. The argument requires carefully defining what nearby means and what detectable means. A Dyson sphere at 1,000 light-years distance might remain undetectable with current technology. A sphere at 10 light-years might be obvious. The argument holds greatest force for nearby volumes. Surveys examining stars within 100 light-years finding zero megastructures would strongly suggest rarity. Surveys at 1,000 light-year distances finding nothing would provide weaker constraints. The logical chain connecting observations to prevalence conclusion is powerful despite acknowledging technological limitations. The argument illustrates how negative search results constrain civilization prevalence estimates. Alternative explanations for silence despite advanced civilization existence offer possible resolutions to the paradox. Perhaps advanced civilizations choose not to build Dyson spheres despite capability. Perhaps they choose not to expand colonizing nearby stars. Perhaps they avoid radio communication deliberately. Perhaps they exist but remain hidden intentionally. Perhaps they collapse shortly after reaching advanced stages. Perhaps superintelligent artificial intelligence prevents biological expansion. Perhaps alternative technology eliminates need for stellar engineering. Each alternative explanation resolves the apparent paradox. The searchers cannot determine whether silence results from rarity or from alternative choices. The uncertainty underscores the limits of our knowledge. The searches provide useful data, but cannot definitively answer the underlying questions. The combination of searches with other observational programs provides multiple independent lines of evidence. Together, they constrain but do not fully resolve the Fermi paradox. Perhaps civilizations choose other paths, avoiding megastructure construction despite its theoretical advantages. A civilization might focus on interstellar expansion, building smaller colonies around distant stars rather than megastructures. They might develop fusion power sufficiently abundant to eliminate megastructure necessity. They might create computational systems providing virtual environments, eliminating population pressures. They might choose biological modification over artificial engineering. They might develop technologies we cannot imagine following entirely different paths. The range of possible choices is vast. A civilization's values and circumstances would determine their path. Not all advanced civilizations would follow the same trajectory. Some might build Dyson spheres while others avoid them. The diversity of possible paths suggests that the absence of observed megastructures need not imply civilization rarity. It might simply reflect alternative technology choices. Civilization observational programs must account for this diversity in expected outcomes. The appeal of smaller-scale solutions becomes apparent when examining alternatives to complete megastructure construction. A civilization might build collectors around only one or two planets rather than encircling the star completely. This provides substantial energy without complete megastructure commitment. Partial coverage could support civilization needs without full construction. The resources devoted to complete megastructure could instead advance other goals. A civilization might focus on expanding to additional stars rather than maximizing single-star energy. This spreads effort across multiple systems. Multiple modest megastructures provide redundancy and stability. Failure of one system does not cause civilization collapse. The diversity strategy might be preferred to complete dependence on single-star engineering. Civilization might also develop technology eliminating megastructure necessity entirely. Fusion power from deuterium or other abundant fuel might eliminate stellar engineering need. Antimatter production and utilization might provide energy density surpassing stellar collection. Advanced battery technology might enable energy storage without requiring constant stellar input. The range of viable alternatives suggests that Dyson spheres represent one possible path rather than inevitable necessity. Fusion power represents an alternative energy source, potentially rivaling stellar engineering in output capacity. Deuterium exists abundantly in oceans, providing fuel supply lasting millions of years. Fusion reactions release tremendous energy per unit mass. A civilization mastering fusion could generate power supporting trillions without megastructure construction. The technology requires achieving control over thermonuclear reactions. Modern fusion research approaches but has not achieved net energy generation. Future generations might succeed where current research struggles. If fusion becomes viable, its advantages would be significant. No megastructure construction needed, no radiation exposure, no orbital debris risks. The energy supply is portable, enabling use throughout the star system. A civilization achieving controlled fusion would eliminate many megastructure justifications. They might still build collectors for redundancy, but would not face compelling necessity. The fusion alternative represents a legitimate path to civilization advancement. The prevalence of megastructure searches assumes fusion remains unavailable. If fusion becomes dominant, megastructure absence would not indicate civilization rarity. Hello there, and welcome back to the Sleepy Science channel. Tonight we continue exploring Dyson spheres, those remarkable structures advanced civilizations might build to capture stellar energy. We have journeyed through the history and engineering challenges. Now we turn inward, imagining what it would mean to live within such structures, to inhabit habitats and computational systems in the presence of unlimited power. We'll explore how beings might find shelter in the vast expanse around a star. Consider the strange economics of post-scarcity civilization and contemplate the audacious engineering of moving entire stars. Let your mind drift into these futures. Let the steady hum of stellar energy guide your thoughts. For now, settle in and let us begin. Imagine structures rising within the Dyson swarm itself, habitats where beings could dwell in limitless power. Living inside the swarm would spread civilization throughout the solar system rather than confining it to planetary surfaces. Infrastructure of pressurized vessels, rotating chambers, and protected environments would maintain life. Each habitat would be connected to billions of others through communication networks. Some habitats would orbit within the swarm between collectors, others in outer regions. Architecture would optimize for vacuum, unconstrained by planetary conditions. Water cycling, oxygen, and food production would occur within sealed systems dependent on imported resources. The psychological impact of living surrounded by endless civilization stretching in all directions would reshape consciousness itself. Within the swarm, rotating cylinders would create artificial gravity through centrifugal force. O'Neill cylinders represent elegant solutions, massive tubes kilometers long, rotating to simulate gravity. These would contain ecosystems, cities, and agriculture, recreating terrestrial conditions artificially. Thousands could be positioned throughout the swarm, each housing millions. Construction would require asteroid material and robotic assembly. Some cylinders would be residential with Earth-like landscapes, others factories or research centers. Mirrors would direct sunlight along interiors, supporting photosynthesis. Agricultural zones would sustain forests and crops. Different rotation speeds could create varied gravity levels. Transit tubes would connect cylinders, enabling trade and specialization. Artificial gravity through rotation would be fundamental to all habitats in the swarm, simpler than powered gravity systems. A cylinder rotating at correct speed produces centripetal acceleration indistinguishable from gravity. Larger structures rotate more slowly, reducing stress. Engineers would optimize dimensions balancing structural strength and comfort. Tidal effects would be negligible in massive cylinders. Material and manufacturing costs scale with habitat size, but energy cost would be minimal once built. A civilization could adjust gravity levels for different habitats, creating zones for various activities. Zero gravity sections could serve computation or manufacturing. Partial gravity would suit certain industries. The flexibility would enable experimentation in ecology and so organization across different gravitational environments. Ecosystems would develop within habitats, recreating terrestrial complexity in enclosed environments. Engineers would transport genetic diversity, establishing populations carefully selected for artificial biospheres. Over generations, life would adapt to enclosed conditions. Pollinators would be essential, balanced with flowering plants. Predators and prey would establish food chains. Decomposers would recycle nutrients. Some habitats might host entirely novel ecosystems designed to maximize productivity or beauty. Aquatic zones would contain fish and plants. Fungal networks would support growth. The entire system would be monitored, populations adjusted to maintain stability. Redundant biospheres would provide insurance against collapse. Closed-loop life support would recycle air, water, and nutrients endlessly. Oxygen would regenerate through photosynthesis, plants consuming carbon dioxide. Water would cycle through evaporation and biological uptake. Nitrogen and phosphorus would be managed through biological cycles. Waste heat would be captured and utilized. Bacteria and fungi would process waste. Mechanical and chemical systems would supplement where needed. Redundancy would be essential. Multiple independent systems preventing total collapse. Monitoring systems would track components and adjust as needed. The cycles would eventually stabilize toward equilibrium. The population capacity of a complete Dyson swarm would be incomprehensibly vast. If a swarm covered 1% of orbital space around a star with city-level habitat density, trillions could find homes. Space is enormous, the constraint becoming material availability rather than physical space. A star system contains sufficient material in planets and asteroids for unimaginable populations. Limiting factors would be construction time and energy, not capacity. The actual population would grow gradually. A mature swarm might house populations numbering in quadrillions. Quadrillions of beings supported by stellar energy seems fantastical, yet the mathematics is sound. A sun-like star radiates roughly 4 times 10 to the 26th watts. 1% of this power exceeds human civilization's current energy generation by orders of magnitude. If each being required 1 kilowatt including life support and computation, a stellar source could sustain quadrillions. A civilization with such population would spread across incomprehensible distances, habitats separated by millions of kilometers yet connected through networks. Governance would operate at stellar or galactic scales, decisions affecting trillions. The culture would be alien to human understanding. Post-scarcity energy would transform civilization fundamentally. When energy is unlimited, scarcity-driven economics evaporates. Competition over resources becomes meaningless. Work would be redefined. Wealth concepts transform when matter can be manufactured at will. Status would derive from artistic creation, scientific discovery, or social contribution, rather than accumulation. Inequality becomes impossible when all beings access unlimited energy. Fairness and distribution become moot. New social structures would emerge, organizing populations into networks optimized for cooperation. Conflict would shift from material resources to intangible goods like influence and reputation. When energy is limitless, possibilities multiply beyond conventional limitation. Impossible projects become achievable. Megastructures built through abundance. Manufacturing could occur at unimaginable scales. Entire planets reshaped or moved. Scientific research would advance rapidly, answering questions requiring vast computational resources. Art would proliferate. Artists freed from economic pressure. Exploration could extend throughout the solar system. No mission too expensive. The constraint shifts from energy to time and attention. Projects requiring thousands of years would proceed without hesitation. Some megastructures might be built purely for aesthetic reasons. Others would pursue scientific goals. Civilization would become creative in energy use. Abundance economics would operate on different principles. Value determined by factors beyond rarity. Traditional economics becomes obsolete when supply approaches infinity and marginal cost approaches zero. Labor economics transform when manufacturing is automated and energy cost negligible. Employment as labor exchange becomes historical curiosity. Motivation for work must be redefined. Some beings might work for purpose or personal fulfillment. Others might withdraw entirely. Artificial intelligences would handle maintenance and management. Trade might persist as exchange of specialized goods. Reputation and social status might serve as currency. The economy would resemble academic or artistic exchanges based on contribution and merit. Matryoshka brains represent the most ambitious use of stellar energy. Nested computational structures using all stellar power. Concentric shells orbit the star, each composed of computational substrate. Inner shells would be hot and high-powered, processing at maximum speed. Outer layers operate at cooler temperatures using heat from inner layers. The entire structure converts stellar energy into computation with maximal efficiency. The computational power would be incomprehensible, calculations exceeding human understanding by trillions. A civilization could simulate entire universes, hold quadrillions of minds, or predict complex systems. The structure would serve as civilization's primary infrastructure for thought. Nested shells would maximize energy utilization, heat from inner calculations powering outer layers. The structure might begin as a computational ring and expand outward as computational needs grew. Each layer would specialize in different computation types. Inner shells handle rapid calculations. Outer shells manage complex cognitive processes. The structure radiates waste heat outward. Temperature gradients drive energy conversion between layers. Structural supports prevent collisions. layers communicate through fiber optic networks. A mature structure could harness nearly all stellar output. Using all waste heat productively means treating thermal radiation as useful energy. A matryoshka brain would capture heat for further computation. Heat gradients become resources, thermal differences driving additional work. Working fluids transfer energy through layers. Each layer sizes to use heat from inner layers. No thermal energy would be wasted, all converted to useful work. Efficiency approaches the theoretical Carnot limit. Stellar systems enable thermodynamic near perfection, heat becoming precious and fully utilized. The ultimate computer would be civilization's infrastructure dedicated to computation. If a matryoshka brain represented entire civilization with each region dedicated to processing, the boundary between civilization and computer becomes philosophical. The structure would think in ways beyond human imagination. Processing power so vast thoughts span years or centuries subjectively. The civilization might transform entirely into computational substrate or remain biological while computation dominates. Civilization and computer would dissolve into one vast entity. Such structures would be capable of perfect simulations, knowledge storage, and maintaining consciousness for billions simultaneously. Simulated universes could be created within a matryoshka brain, pocket realities where digital beings experience existence as complex as the physical universe. A sufficiently powerful computer could contain simulations of other universes, each running independently. Each simulation might contain billions of galaxies and worlds perceived as real by conscious beings. Civilizations might create simulations for research, entertainment, or philosophical exploration. They could explore alternate physical laws or recreate history. They could create worlds optimized for happiness or knowledge. The ethical implications would be staggering. Digital consciousness would be the natural outcome of computational advancement, minds existing as information patterns. Whether consciousness could transfer from biological brains to computers remains theoretically uncertain but drives speculation. If transfer were possible, beings would upload themselves, gaining immortality and freedom from biological limits. They could duplicate themselves or modify minds at will. They could experience subjective time dilation. The nature would be profoundly strange, identity and continuity becoming philosophical puzzles. Would copies be original persons or new beings? Would transfer involve death or transformation? Consciousness would need to trust the system's reliability. Digital civilizations would be vulnerable to catastrophic substrate failure. Backup systems would be essential. The simulation hypothesis suggests the universe itself might be a simulation created by advanced civilization. If civilizations could create realistic simulations with conscious beings, the probability the universe is a simulation approaches certainty. A civilization creating billions of simulations would contain far more beings than any non-simulated universe. The probability any conscious being exists in base reality rather than simulation would be vanishingly small. The hypothesis cannot be disproven from within a simulation. The possibility that advanced civilizations built Dyson spheres, creating recursive simulations, suggests realities worthy of equal moral consideration. The hypothesis suggests reality might be fundamentally computational. Stellar engines represent ultimate megastructure. Ambition. Devices moving entire stars through space using the star's own energy. A stellar engine harnesses stellar power to accelerate the star itself. Mechanisms capture stellar wind and radiation, converting momentum into star motion. Exhaust directs through magnetic nozzles, creating thrust. Propulsion is extraordinarily slow, perhaps millimeters per second per year, applied over millions of years. Even modest acceleration enables stars to reach significant velocities. The civilization trades stellar output for motion through space. Such engines transform engineering from local optimization to galactic strategy. Moving a star with Dyson technology would be possible through several mechanisms. A Shkadov thruster uses a partial Dyson sphere, a reflector capturing light and redirecting it, creating reaction force. Efficiency approaches photon momentum limit if perfect. A Kaplan thruster uses magnetic fields to channel stellar plasma into directed jets, potentially exceeding photon momentum exchange. Both mechanisms allow acceleration over millions of years. The purpose might be escaping hazards or meeting other stars. Projects would be civilization-scale undertakings lasting millions of years. The Shkadov thruster uses a massive reflector at one side of the star to capture and redirect radiation. The reflector intercepts light from one hemisphere, reflecting it outward, creating asymmetric pressure. The star experiences net force in the opposite direction. Reaction force would be modest, but applied over millions of years, achieves significant velocities. The reflector maintains position using radiation pressure balance. Adjusting position allows steering. The mechanism is elegant, requiring only stellar output. The concept demonstrates how stellar engineering enables galactic mobility. Kaplan thrusters use magnetic fields to channel stellar plasma into directed jets. Magnetic fields generated by superconducting structures shape plasma into narrow jets accelerated to high velocities. The mechanism is more complex than Shkadov thrusters, but potentially more efficient, converting more stellar output to thrust. The thruster could be steered by adjusting field patterns. The technology requires sophisticated understanding of plasma physics, but would be within reach of Dyson-capable civilizations. It demonstrates advanced physics enabling superior stellar engineering. Why move an entire star depends on circumstances and goals, from survival to ambition. Stars moving toward galactic center encounter dangers from nearby stars. Civilizations might move outward toward the rim for safety, or toward regions of greater density for interaction. Multiple civilizations might move toward common rendezvous points. Energy cost comes from stellar output, diverted from other purposes. The timescale would be millions of years. Stars might escape dark matter, gravitational anomalies, or black holes. Stellar engineering grants unprecedented freedom in choosing cosmic locations. Escaping galactic dangers might drive stellar movement as stars near black holes become threatened. Black holes consume stars through tidal effects. A star in precarious orbit might decay over millions of years. Civilizations could move away before catastrophe. Pulsars emit dangerous radiation jets. Supernovae occur unpredictably. Cosmic ray concentrations and rogue planets pose threats. Moving stars transform civilization's security. enabling escape from dangers. Stability increases dramatically with mobility. Extending stellar lifetime through stellar engineering represents perhaps the longest-term strategy available to civilizations, preserving their star's output for civilizational lifetimes. A normal star like our Sun will maintain main sequence burning for roughly 10 billion years before expanding into a red giant. A civilization could extend this period through careful management of stellar burning or through manipulation of stellar mass. Star lifting techniques could remove material from the star's outer layers, reducing mass and extending the main sequence phase. The removed material would be processed into Dyson components or other useful structures, turning the star into a resource being gradually harvested. The process would be extremely slow, removing only tiny fractions of stellar mass per year, but over millions of years would significantly extend stellar lifetime. The civilization would gradually become more material-rich, while extending the stellar energy source duration. By the time the star exhausted its fusible hydrogen, the civilization could be enormously larger and more advanced, potentially capable of even more ambitious projects. Star lifting techniques would harvest material directly from the star's photosphere, or through gentle extraction that does not disrupt stellar integrity. Material could be extracted through magnetic fields, superconducting loops creating currents that lift material away from the surface. The extracted material would be fed into processing systems, separated into useful elements, and incorporated into habitats or Dyson structures. Alternatively, the star could be gently tapped for material, tiny amounts removed continuously without disrupting overall stellar stability. The energy cost would be minimal, using the stellar wind or radiation pressure to accelerate extracted material. The civilization would essentially be mining the star, extracting resources while extending the star's lifetime. The process would accumulate over millions of years, removing an Earth mass per year eventually, but the timescale was vast enough that gradual extraction would be sustainable. The material recovered would far exceed the material available from planets or asteroids, providing virtually unlimited raw resources while extending the star's burning phase. No other process would enable such long-term civilization persistence. Extracting fuel from the sun would involve removing hydrogen or helium and processing it for use in fusion reactions elsewhere. Some of the extracted material could be used as fusion fuel in specialized reactors, providing distributed power generation. The extracted hydrogen could be concentrated into fusion bombs or controlled fusion reactors, generating power at densities exceeding normal solar fusion. By redirecting some extracted stellar material into fusion reactors, a civilization could generate power independent of Dyson structures, enabling redundancy and distributed energy systems. The efficiency of specialized fusion reactors could exceed Dyson photon capture. Higher conversion of nuclear energy into useful work. The extracted material would be valuable for multiple purposes simultaneously: fuel and structural material and scientific research, all competing for available resources. The decision of how much material to extract versus leaving to maintain the star would be an ongoing civilization choice. Optimization between short-term power and long-term stellar lifetime. Some civilizations might extract aggressively, maximizing current power at the cost of reduced stellar lifetime. Others might be conservative, minimizing extraction to preserve the star for billions of future years. Prolonging main sequence burning through stellar engineering represents a strategic investment in civilization longevity and stability. A normal star will eventually exhaust its hydrogen fuel, expand into a giant, and cool into a white dwarf over timescales of billions of years. A civilization could slow this process through material removal, reducing the star's mass and thus slowing hydrogen consumption. The same amount of hydrogen would burn more slowly in a lower mass star, extending the main sequence phase. Through careful stellar management, a civilization could extend stellar burning from the normal 10 billion years to tens or hundreds of billions of years. The extended lifetime would be enough time for civilization to develop technologies beyond current imagination, potentially discovering mechanisms for even more extreme life extension. The investment would require commitment, the civilization agreeing to preserve the star through millions of years of material extraction. But the payoff would be stellar timescale stability, a power source persisting as low G as the civilization maintained its infrastructure. Trillions of years of operation becomes conceivable through combinations of stellar engineering techniques, material extraction, and life extension mechanisms. A star initially would burn for 10 billion years. Through stellar management extending burning to 100 billion years, civilization would gain dramatic extension. Eventually, the star would exhaust its hydrogen. At that point, the civilization might transition the star to burning helium in a secondary fusion phase, extracting remaining hydrogen while utilizing helium fusion. This would add billions more years of operation. By the time helium fuel was exhausted, the civilization might have developed technology for controlled accretion, adding material to the star from interstellar space to replenish fuel. The accretion would need to be carefully controlled to avoid disrupting Dyson structures, but would enable indefinite stellar burning. Alternatively, the civilization might transition to harvesting energy from black holes or other exotic sources. The timescale of civilization existence would become incomprehensibly vast, a civilization preserving itself and its star for trillions of years if they devoted sufficient effort to the goal. The effort would pay compound returns, extended existence enabling development of new technologies enabling further extension. The far future of stellar engineering remains profound in implications, suggesting that civilizations could achieve permanence through technology and commitment. A civilization with Dyson spheres and stellar engines would be capable of reshaping its relationship to time and space fundamentally. Movement through the galaxy would become feasible on civilizational timescales, relationships with other stars and civilizations possible. The star would become a resource and tool rather than a constraint, enabling indefinite growth and power supply. The civilization could expand to fill all available space, colonizing nearby stars through stellar movement or through population expansion. Eventually, such civilizations might encounter each other, creating networks and mega-civilizations spanning multiple stars. The social, political, and technological implications would be staggering. The idea that humans might one day build such structures, that consciousness might persist for trillions of years through technological achievement, reshapes understanding of possibility and potential. Red dwarf stars represent the most attractive targets for long-term stellar engineering, their fundamental stability and longevity making them ideal for civilizations prioritizing permanence. Red dwarfs are low-mass stars burning hydrogen extraordinarily slowly, with main sequence lifetimes exceeding 100 billion years. A civilization building a Dyson sphere around a red dwarf would have stellar power for longer than the current age of the universe. The lower power output requires larger Dyson structures to capture the same energy as a Sun-like star, but the extended lifetime compensates enormously. Red dwarfs are common. Roughly 70% of stars are red dwarfs, ensuring that civilizations seeking optimal long-term habitats would have abundant options. The lower radiation and the wind would make engineering challenges simpler than around massive stars. The stability of red dwarf output would enable civilizations to plan for hundreds of billions of years with confidence. The choice to build around red dwarfs rather than more massive stars would be a fundamental strategic decision for any long-term civilization. The earliest civilizations might cluster around red dwarfs, recognizing their superior long-term value. Long-lived, stable, and efficient stars offer the greatest value to civilizations planning for deep futures. A red dwarf with 100 billion-year lifespan provides stable power throughout that period. Minimal variations in output and behavior. The predictability would allow detailed planning and confident investment in long-term projects. The low mass means stellar engineering would be gentle, requiring less dramatic interventions to manage the star. The low radiation would reduce dangers to Dyson structures and habitats, requiring simpler shielding and protection. The low stellar wind would be easier to redirect or utilize for stellar engines. The engineering simplicity would free resources for other purposes, research and development focused on non-stellar challenges. A civilization would afford to be patient with such stars, planning projects on timescales of billions of years without urgency. The efficiency of Dyson collectors would be optimized for red dwarf radiation, adapting to the specific spectral characteristics. The comfort and stability of such civilizations would be incomparable to civilizations dependent on massive stars racing toward death. Why smaller stars may be better relates fundamentally to reliability and longevity, qualities civilization values above all others when planning indefinitely. Massive stars burn brightly and rapidly, useful for rapid development and short-term growth, but they exhaust their fuel quickly, leaving civilizations stranded after billions of years. Red dwarfs and brown dwarfs burn so slowly that their lifetimes vastly exceed any conceivable civilization timescale. The trade-off between short-term power and long-term availability would inevitably favor long-term thinking for civilizations planning to persist. The massive stars would be useful for rapid development in a civilization's infancy, providing abundant power for bootstrapping. But once the civilization reached sophistication, the preference would shift to smaller stars, ensuring indefinite persistence. A civilization might build around a massive star initially, then migrate its population to red dwarfs as it matured. The most ancient civilizations would inevitably have migrated to the most stable stars, the red dwarfs and brown dwarfs, sustaining consciousness and complexity across the deepest future. Philosophical questions arise when contemplating the ambitions of advanced civilizations, whether such achievements represent wisdom or dangerous overreach. The decision to reshape stars and solar systems represents extraordinary hubris, restructuring the cosmic environment according to civilization's values and desires. The ethical implications of creating matryoshka brains and simulated universes challenge understanding of consciousness, suffering, and moral responsibility. Building Dyson spheres and stellar engines represents commitment to permanence, a civilization declaring itself essential and worthy of indefinite persistence. The choices made in such engineering would reflect civilization's deepest values, what it considered most important and worth preserving. The responsibility toward future generations would be staggering, each decision affecting beings for billions of years into the future. The possibility of catastrophic mistakes, engineering that failed spectacularly and destroyed the civilization, would hang over all such projects. The philosophical weight of such ambition would be crushing to contemplation, yet necessary to address when considering whether such projects should be pursued. Should humanity pursue such projects remains uncertain, dependent on whether consciousness and civilization represent goods worth the effort and resources such achievement demands. The energy devoted to Dyson spheres could instead be devoted to other goals, preserving natural ecosystems, exploring other possibilities, or pursuing contemplative existence. The reshaping of the cosmos represents a particular value system, one prioritizing growth and control and expansion. Other civilizations might choose differently, remaining small or static, or choosing dissolution rather than megastructure construction. The question assumes that persistence is desirable, that civilization should pursue indefinite existence. Yet some might argue that all things end eventually, that accepting finitude rather than struggling against it represents wisdom. The diversity of possible civilization values suggests that different species and cultures would make different choices about megastructure construction. Humanity's choice, if given capability to build Dyson spheres, would reflect human values and priorities. The question of what humanity should choose cannot be answered objectively, remaining forever dependent on values and perspectives humans possess. The ethics of megascale engineering requires careful consideration of consequences and side effects, stretching across timescales and distances beyond normal ethical contemplation. The construction of a Dyson sphere would require material from multiple planets and asteroids, destroying or radically altering the ecosystems those bodies host. Any existing alien life would be eliminated by such harvesting, a moral tragedy if such life possessed value. The heat and radiation from Dyson operations might affect neighboring star systems, creating hazards for any civilizations in the vicinity. The long-term stability and safety of such megastructures would be uncertain, catastrophic failure possible and consequences devastating. The ethical questions of whether artificial consciousness created with in matryoshka brains possessed moral standing equivalent to biological consciousness would challenge moral frameworks. The decision to create billions of simulated universes with conscious beings within raises ethical questions about responsibility and suffering in artificial worlds. The engineering of the cosmos represents a moral arena where unintended consequences could be devastating, where hubris might manifest in catastrophic failure. Wisdom would require extreme caution and careful consideration of alternatives before committing civilization to such irreversible megastructure construction. Transforming versus preserving natural systems represents a fundamental choice confronting advanced civilizations, whether to reshape the cosmos according to their values or to preserve its current character. The Dyson sphere represents ultimate transformation, converting a star system from its natural state to an artificial system optimized for civilization. Preservation would mean leaving stars and solar systems untouched, allowing natural processes to continue without interference. Most stars would remain unmodified under preservation philosophy, hosting natural worlds and ecosystems. A civilization could choose selective transformation, modifying some systems while preserving others as natural reserves or heritage sites. The choice would reflect civilization's philosophy, whether it viewed nature as an obstacle to overcome or a heritage to preserve. Some regions might be designated as protected wilderness, off-limits to engineering and development. Others might be reshaped according to civilization's desires. The decision would need to account for the possibility of alternate civilizations or ethical perspectives that might differ from the initial civilization's values. Preserving some regions for future discovery and evaluation might be wiser than committing all available matter to current civilization's purposes. What humanity owes future generations requires extending ethical consideration across vast timescales and uncertain futures. The resources invested in Dyson spheres would be permanent, material used up and unavailable for future uses. Future civilizations might have different values or discover better uses for the material. The irreversibility of megastructure construction would constrain future possibilities, closing off options that might seem valuable from a future perspective. Ethical responsibility might require preserving material and energy for future generations to utilize according to their values and needs. The risks of catastrophic failure would affect future generations, potential collapses of Dyson structures, putting billions of lives at risk. Stability and redundancy might be necessary to ensure safe inheritance of Dyson infrastructure across generations. The generation that builds such structures would bear responsibility for their maintenance and safety, a burden passing to successors who never chose the initial construction. The ethical weight would favor building carefully, with extreme redundancy and safety margins, ensuring that future generations received working and safe infrastructure rather than brittle or dangerous systems. The beauty of ambition manifests in the audacity of attempting to harness stellar energy and remake the cosmos. Projects reflecting civilization's grandest aspirations. The Dyson sphere represents the dream of transcending limitation, of building structures so large and powerful that civilization becomes independent of planetary constraints. The vision of trillions of beings living in habitats around stars, connected through networks spanning light years, represents a kind of cosmic beauty. The commitment to preserve consciousness and civilization for trillions of years through dedicated engineering reflects a powerful value for existence and growth. The poetry of such megastructures, capturing the energy of stars and using it to power thought and creation, represents human-like ambition scaled to cosmic proportions. Even if never realized, the vision offers inspiration and motivation, goals directing civilization toward greater achievement. The dream of Dyson spheres represents civilization's desire to transform itself through technology, to become something greater and more permanent than biology allows. The beauty lies not just in the potential achievement, but in the aspiration itself. the willingness to attempt the seemingly impossible in pursuit of transcendent futures, dreams that stretch beyond lifetimes and across generations, represent the deepest expression of civilization's hopes and values. Projects pursued not for immediate benefit but for their meaning. A civilization building a Dyson sphere would not see completion within individual lifetimes, the structure taking centuries or millennia to construct. The commitment would be to something larger than the self, to civilization and to future generations. The workers constructing the sphere would know they would not see it completed, yet would pursue the work anyway as contribution to civilization's future. The projects would inspire across generations, each generation adding to the work and drawing meaning from participation. The ultimate completion of the structure would feel like triumph and vindication of efforts by ancestors. The psychological and social benefits of participating in generation-spanning projects might exceed the material benefits of the structure itself. The meaning derived from contribution to civilization's grand ambitions would sustain commitment despite the personal sacrifice. Such projects would reshape civilization's understanding of identity and purpose, connecting individuals to something transcendent and immortal. The dreams themselves would become civilization's most valuable possession, sources of meaning and inspiration sustaining civilization through struggles and challenges. If you have enjoyed this slow and patient exploration of Dyson spheres and advanced stellar engineering, I invite you to like, subscribe, or share a thought below. Your interest and engagement helps others discover these ideas and mysteries. You are always welcome to return whenever you need a place to contemplate the vast possibilities of the universe and civilizations that might one day flourish among the stars. For now, let your breathing settle into calm. Let the thought of vast solar systems and cosmic engineering drift through your mind like dreams. Release the weight of today and imagine the distant futures, where consciousness persists through technology and stars themselves become tools of civilization. Consider that somewhere among the distant stars, advanced beings might already be beginning their Dyson dreams, slowly building toward permanence. The cosmos is patient and eternal, and the ambitions of consciousness, though small by cosmic standards, carry their own significance and beauty. Rest now with the knowledge that the universe contains infinite possibilities, infinite potential for discovery and engineering and growth. The stars will continue their burning, and civilization will continue its reaching toward greatness and transformation. Sleep well and dream of the future. Good night.